All right, welcome everybody. Final day here, huh? So this is the last day, day 5. Got some really good stuff to talk about here today. The Greeks, delta hedging, exotic options. Still be talking about that risk neutral pricing stuff again. So, we got a lot of good stuff to talk about. I'm hoping that you've found that these have helped you not just like to remember formulas, but like to kind of understand the core of everything. Like that's really what we're aiming for with these, and to have like kind of a good system to solve problems that can alleviate some of these struggles that we have because this test is so binary. It's like so many things where it's like, it's either call or put. It's either do I buy or do I sell? Do I go long or short in this? Like, but hopefully we've kind of built up some machinery to help you to kind of keep track of all that and let the math take over for you so that you don't have so much to think about. That's kind of really, as math people, that's really what we do anyway, right? Like quadratic formula, we don't rederive that all the time, right? We trust it, we use it, and we don't even really think twice about it. So we want that same sort of balance here. We don't want to try to have to like think through everything from the very beginning from scratch. We kind of want to have this like healthy balance of being able to do that, but also let the math do its part for us too. And we're going to see the whole thing with like the portfolio with plus long, minuses shorts. We're going to see that's going to really help us when it comes to delta hedging. Some of these really tough problems for delta hedging become really easy because of that. Okay, so we'll get to that today. So, all right, so let's get started here. So let's talk about the Greeks first. So the Greeks are, they're a way for us to kind of being able to say something about option prices, or it doesn't have to be just calls and puts. It could actually be anything more general. Most of the time it's calls and puts, but especially because the Black-Scholes formula is like really complicated, right? It's the prepaid forward on the S times N of D1 minus, prepaid forward of K, N of D2 for calls. And there's like so many parameters in there. There's like current stock price, there's the interest rate, there's delta, there's like the dividends, there's time, like all these factors go into that price. And we'd like to know some sort of way, like, is there anything I can tell about the option price if we sort of tweak some of those parameters? That's what the Greeks are. For the most part, that's really what they are. Now, the only parameter that it doesn't really deal with is K, but we sort of dealt with that already, right? Like if you increase the strike for a call, the price actually goes down, or if you increase the price for a put, the price goes up. That was that whole diagram where for a call, it sort of looked like this, and for a put, it looked like that. I think we talked about it maybe seminar 2 or 3 maybe, but so that was if we switch K, if we adjust K. But the rest of the Greeks here are about the other parameters. Okay, so we're going to use V as like just the value of an option, just to keep it neutral. It could be a call or a put, or it could actually be a portfolio that entails calls and puts. But yeah, we just want to see like, okay, what do the different Greeks mean, and how can they help us, and like how do we compute them? Now, a lot of this stuff, by the way, is on the formula sheet. So if you have your formula sheet, you can kind of get it out. There's like a list of tables and stuff like that for the IFM. And if you want to, you can kind of grab it out. Yeah, you could totally just grab that out, the formula document. It's in fact, if you want to Google it right now, you can, just to kind of follow along a little bit. But it's the same thing if you got like, coaching actuaries, TIA, they have like the exhibit thing. It's just the thing that you'll be given on the test. But I did want to draw your attention to a few things on there. I put them here, how you see them on the formula sheet in these sort of blue boxes, and we'll see what we can gain from that. Okay, but first of all, okay, let's talk about delta. Delta is the most important. Delta is the most used and most helpful feature, because it deals with the thing that changes the most. And that is, it tells us the change in option price compared to the current price. Now, what they'll do here, by the way, is sometimes they'll not say, it's actually S0, but usually in the formulas, they just actually put like S. But I don't know, I found that kind of confusing, because I'm like, S when? Like ST or like S0? But it is just like how we did on the other seminars. If they don't really put a subscript, it's usually S0, current stock price. Okay. And that's what it is. So it tells us how the option changes compared to how the stock price changes. In other words, for every dollar that the stock goes up, how much should the option go up? That's really what it's saying. It's like change in option per change in stock. So per dollar change in stock, how much should the option go up? And if it's negative, then the option would actually go down, right? It would lose value if the price goes up, the current stock price. And this is, so these are actually like a multi-variable calculus thing. It's really just the derivative. So you might even see it written like this. It's not technically proper because the dvds means that there's only one variable. But to me, I don't know, it's easier to draw and it's kind of quicker and it's not just so annoying. So I'm probably going to write this, even though mathematically I could, get really in trouble in the math circles. But I'm going to write this just because it's easier. We get the idea. It's really the derivative, change in V over change in S, right? That's how we want to think of it. So that's delta. Now we'll find out that delta for a call is always positive, but less than 1. And delta for a put is negative, but always, not worse than a -1. It shouldn't be. Okay. Now we can actually ascertain that from the formula sheet. So if you have the formula sheet, you can look at it, but it says for delta, this is the formulas they give us. Now here we know n is a probability, so it's always between 0 and 1. And then if I multiply by e to the negative delta something, well, it's just going to shrink it maybe a little bit more. So it's definitely always going to be between 0 and 1 and positive. But the put is negative and, well, a similar sort of thing. N of, negative d1 is still a probability. So it's between 0 and 1. And then, shrink it maybe just a little bit more, but still definitely between a -1 and a 0. So we can kind of tell that just from there anyway. And so what does that mean? Well, if the delta is positive, like for a call, that means for every dollar the stock goes up, the option will increase by, some amount by delta. So maybe if it's like a 0.6, then it says like, oh, for every dollar the stock goes up, the call should increase by 60 cents. Okay, and if it's negative, then like, let's say a -0.8 or something like that, that means, okay, every dollar the stock goes up, the option decreases by 80 cents. So that would be like for a put. A put would make that the case. And that kind of makes sense too anyway, because you're like, well, if I, fix the strike, then so for a put, let's say, why would the value go down? Well, because if I fix the strike, but the current stock price goes up, well, it's kind of now putting you in a position where it's just that much harder for the put to end up paying out. So the put will become less valuable. And specifically how much less valuable? Well, that's what delta tells us. Okay, but that's the idea. That's the idea behind it. Now, one of the biggest things that's actually really helpful for us with all these Greeks is the put call parity. Right? We're gonna show that there's some really cool things. Some of the formulas that they give already kind of have this in there, but some of them don't. Like from here, it's not really clear to see how delta for a call and delta for a put relate to each other. But the put call parity is going to help us to like be able to get that no problem. We're going to see how these relate to each other real easy. I mean, they look sort of similar, but then you're like, well, this is like an n of negative d1, but that's a positive, and like those are kind of weird. Like they're related, but it's not real clear how. So what do we have here? So, all right, well, here's the put call parity. Call minus put is, SE to negative delta time, and then KE to the negative R times time. And so if I wanted to find out what this was with deltas, well, the deltas are just the derivative with respect to stock price. So I'm going to say the derivative with respect to stock price, and I'm going to take the derivative of this whole equation. We know how that works with calculus, as long as it's a sum or a difference, you could just kind of do each term, no problem. So the derivative of call with respect to stock price, that is delta call. Derivative of put with respect to stock price, that's delta put. How about this, the derivative of this with respect to S? Okay, well, it's actually just S times some number, so it's almost kind of like 2S or something like that. So if I took the derivative with respect to S, what would I get? Well, I would just get the constant. So this is just going to be e to the negative delta times time. And we're going to see that we're using this slightly like more verbose formula Sometimes it could just be like kind of times a t. But here we're going to do t minus t because it's going to be important for one of the Greeks specifically. But that's okay. It's just a different way. A lot of times we think of little t as just being 0 anyway, but no problem. All right, what about the derivative of this with respect to s? And if you think about it with respect to s, well, all that's just a big constant. Derivative of the constant is 0. And so I just get this. So this is kind of interesting. Not even, I don't think you really have to memorize it because it's actually almost immediately clear if you just remember put call parity. You're like, oh, call minus put is, SE. Oh, if I took the derivative with respect to S, great. Delta call minus delta put is equal to, okay, well, it's S times, so e to the negative delta times time. So this actually shows us how the delta for a call and a delta put are related to each other. And if you put these in, maybe you could try this a little bit later, but if you put those in there, you'll actually see that it does become e to the negative delta times t minus t. So you could try that a little bit later. Or maybe if I end up talking too much, you can even do it now. So you can do it there. And then one more thing that we're going to need for when we do delta hedging is, what is the delta for a stock? So the delta of anything is the change in it compared to stock price. And we wanted to know specifically delta for what? Well, delta for stock. So basically it's saying, oh, how much does the stock price change if the stock price changes, by $1? And you're like, well, when does this change by $1? And the answer is, yeah, you can almost think of it as like those cancel out, just get a 1. But yes, the delta for a stock is 1. Okay. So it seems a little silly, but it's going to be super important. All the other Greeks for a stock are actually going to be 0, which is a little bit weird, but we'll kind of show it along the way. And then gamma, well, gamma is another one here. So gamma is actually the change in delta compared to current stock price. So that would be like basically like a second derivative then, right? The second derivative of B with respect to stock price. So that's the way that they write it. D squared V over DS squared. It's just like DS twice, take the derivative with respect to S twice. Now from the formula sheet, here's what they say. The delta for the call and the delta for the put, they're both the same and they're both equal to this. So we actually see that delta call equals delta put, and we can see, well, everything here is positive. So, well, both of them are going to be positive. So the gamma is always positive. Okay. And if we didn't know that, that's okay. We could kind of use what we found on the previous page, delta call minus delta put. And if we wanted to find out how the gammas are related, we could take the derivative with respect to current stock price. And if I do, okay, derivative of delta call with respect to stock, well, now that's the second derivative, so that's gamma call. And the derivative of delta put with respect to stock price, now that's the second derivative of the put, so that's gamma put equals, and now what's the derivative of this with respect to S? Well, it's a constant, so derivative is 0. And that shows us that they're equal. Delta or gamma call equals gamma put. Now, they already gave us the formula, but I want to derive it because there's a couple of valuable things that we can learn from it. Now, like I said, they've already given it to us on the formula sheet, but I've seen questions where, like, sometimes they ask you for the delta of a gap call or a gap put. And for that, you have to kind of perform the derivative manually by yourself for something. Right. So I just wanted to see kind of where these pieces came from, especially this like NPrime of D1, like what does that even mean? And like kind of where does this come from? So, well, so let's just do it. So we'll do it for a call just to kind of to show you how it works for a call. But so really, if I wanted the gamma for the call, it's just going to be the derivative of delta with respect to S. And from the previous page, we found that delta was this. That's just the thing on the formula sheet. Delta or e to the negative delta times time times n of d1. That's the thing that's right here. So e to the negative delta times time to n of d1. All right, and now I want to take the derivative of this with respect to s. So with respect to s, how do I do that? Well, this is just a constant, so I'll bring it along. Since it's a constant times something, e to the negative delta times time. But now the derivative of n of d1. So the chain rule says this isn't a constant with respect to s. In fact, I remember d1, the formula, it looks like this, right? log of S over K plus the R minus delta minus plus 1/2 sigma squared times time over sigma squared to time. So that's my D1. It's a function of S. So I can't just kind of take the derivative. It's just a big constant. So the way that we did this in calculus, it says, oh, I'll do the derivative of the outer thing and then plug the stuff back in. But then I need to multiply by the derivative of the inside. So this is maybe not the way that you've seen chain rule before, but this is actually the legal definition of the chain rule. Because you're like, well, I want to do the derivative of a function of a function. But this is how you do it. You just do the derivative of the outer one and put the stuff back in, and then multiply it by the derivative of the stuff that wasn't just an x. So we got that. So the big thing here now for me is I'm going to need to take the derivative of, the derivative of D1 with respect to S. Well, that's okay, no problem. So I could do the derivative of that with respect to S. So here it is. I'm just going to rewrite it a little bit just to make it a little easier. So I'm going to pull the sigma square roots of t minus t. I'll just kind of pull that out front as a coefficient. And then I'm going to split the log up into log S minus log K plus all the other stuff. So all the other stuff, all that's kind of like a constant. So really, all this stuff is a constant. Even if I multiplied it through by this, it would just be a big constant. So that's all, the derivative of all that's just going to be a 0. And so I'm really just doing, well, the derivative of log S. And that's 1 over S. So I'm going to have here that this is just 1 over S and then times the square root of sigma square roots of time. All right, that's the derivative of D1 with respect to S. So that's nice because that's my only missing piece over here. 1 over S sigma square roots of time. So I'm basically just going to have all this over that. So I'm going to have e to the negative delta times time and primed of D1 over S sigma square roots of time, which is the formula they got. Same thing there. And I want to talk about the N prime, but any questions about that so far? Doing some of these derivatives is like really complicated, but the good thing is that you don't really need to do that. Like you're not really responsible for that, which is nice. All right, so let's talk about the N prime. Now they actually, let me just look at the formula sheet. I think they actually give you N prime also. Yeah, okay, so notice on the first page, if you're there, halfway down it says the standard normal's density function fz of x is just n primed of x. So I just want to kind of explain that real quick here. We know what n of x was. That's the thing we use the calculator for on the on the exam, the computer or whatever to do that. But basically it's just the CDF for z. That's when we're like, oh, probability that z is less than x. So what it is it's the integral from negative infinity up to x of the density of the standard normal. So it's the density of the standard normal, that's, well, 1 over square root of 2 pi. This is something back in P, but it never really came up. So e to the negative z squared over 2 dz. So z squared over 2. But what I'm trying to do is I'm trying to do the derivative of that. So what is the derivative of this thing? So n primed of x, and really we're just saying the derivative with respect to x. That's all we are. So I look over here and I'm like, oh, what is the derivative of this with respect to x? And well, I noticed that the x is the upper limit. And remember back in calculus when you did the derivative of an integral, they kind of just cancel it out. But actually this, because that's the parameter, that I would just kind of replace that in for the variable that's in here already. So this 1 over square root of 2 pi e to the negative, well, it'll just be x squared over 2 now. So this is 1 over square root of 2 pi. So I kind of basically just kind of remove the integral because I'm doing the derivative of an integral. They kind of cancel each other out. E to the negative x squared over 2. And that's actually what they say on the formula sheet. They're like, okay, and then they're like, it's just e to the negative x squared over 2 over square root of 2 pi, and then they give you kind of like an approximation. It's honestly, it's just easier just to do the pi. So just put that in, just use the pi. I think that's easy enough. And so what that means is then if I wanted to know n primed of d1, all that means is I'm just going to plug in d1 in for x. So it's going to be 1 over square root of 2 pi e to the negative, and then d1 squared over 2. That's it. That's all I'm doing. So I'll first compute out d1, store it into like x or something like that, and then just do 1 over square root of 2 pi e to the negative, well, that's squared over 2. All right, so sometimes when we look at this, we're like, wait, negative, like, oh, am I doing the derivative with respect to d1 or something like that? Like, I don't know if you've kind of thought that, but no, we're just doing the derivative of it without anything and then plugging in d1 for like for the x. That's all you're doing. Okay, just want to explain that because I remember I was like super confused when I first learned it. So, okay, that's gamma, and okay, theta is the other big one. So the delta, gamma, and theta are the most important. Delta is the most important, and then gamma, theta are also pretty important. The other ones don't really come up that much, but you still want to know about them. So theta now. So theta. Theta is an interesting one because we think of theta is t, which is time. So we're actually doing the derivative with respect to time. See how the option changes with respect to time. All right, now here's those where we kind of need this this more verbose description here. So by the way, just for a vote, I mean, if you want, so it's either with respect to little t or capital T. So maybe, so let's vote here. Which one do you think it's going to be with respect to? So we'll say yes for little t or n for big T. So which derivative do you think it's going to be with respect to, little t or big T? And just kind of see what you think. Because it's going to be with respect to one of those two times. We just need to know, like, yeah, like which one. So what do you think? All right, okay, great, okay, good. Thank you so much. Thanks for the feedback. So, okay, so here's the idea. So if we said it was with respect to, let's say, big T, we'll do that one first. So if we said it's with respect to big T, then we're kind of thinking like, oh, what happens if big T changes? So in other words, like what if we extended out the expiration? Now that feels a little bit weird since these are European options and the expiration is fixed, right? So it kind of feels a little bit weirder. I mean, it's okay, I guess, but then if we said the derivative with respect to that T, that means like, oh, as it gets longer and longer, what should we expect the option to change by? And I guess that would be okay, but it may not be the thing that we really is the most practical for us. Versus if I take the derivative with respect to little t and I say, okay, what happens as little t moves forward? Now we're actually saying like, oh, okay, how does the price change as I get closer to the expiration? So I'll still anchor the capital T, but I'll say like, okay, what happens as I get closer and closer to expiration? That feels a little bit more helpful, doesn't it? Because what that means is if I know the theta at any moment, I can say like, oh, okay, as time passes, I know what's happening to this call. It's either going to go, or this put, it's either going to go up or down in price as I get closer to expiration. So it's actually little t is the one we want to do the derivative with respect to. And that's why we had to introduce this kind of like more explicit notation here. It's for the theta. Because the time I need to know like, okay, usually we think of we're always at time 0, but actually we want to think of like as we creep closer to expiration, what happens to the option price. So that's how we're kind of thinking about this. We want to know what happens as we get closer to expiration. And that's why we use little t, not big T. But great, yeah, thanks for voting, appreciate that. So we can kind of do the same thing we did before. Okay. So I have a question too. Is it correct to explain that little t is the correct one because it's capped by capital T? Oh, so it doesn't go any further than this? Yeah, that's good too, yeah. So little t will never go past capital T because capital T is just anchored. It's fixed. It's a European option that has an exact expiration date. If you were talking about the expiration changing, now it's a whole different option, right? Everything changes now. So, but yeah, good. So we just want to think of this as fixed. This is never changing. That capital T is anchored in time. The only one that is changing realistically is that one. So yeah, great. Yeah, good question. So we can do the same sort of thing we did before. We could do the derivative with respect to little t now, do the put call parity, derivative with respect to little t specifically. So now we're doing theta of call minus theta of put is, all right, the derivative of this with respect to little t. All right, well, we know how to do the derivative of anything with an e to the something in the exponent, right? We're just going to copy it straight down. So I'm going to go s e to the negative delta times t minus t. But now I have to do the derivative of the exponent with respect to little t here. And what is the derivative of this with respect to little t? When I factor, I'm going to have a minus delta capital T, so the derivative of that's a 0. There's no little t there. But then as I distribute into the second, I have a negative delta times negative t. That's a positive delta t. Derivative with respect to t is just positive delta. So I'm just going to write it out front there. Delta s e to the negative delta times time. And this one's a little bit special because the t is in both of these terms. So now when I do the derivative of the second one, I'm also going to end up with stuff. So, but again, the t is up in the exponent. So I'm just going to copy it down. Oops. Ke to the negative r times time. But then times the derivative of the exponent with respect to little t. And for the same reason, we're just going to get a positive r coming out of there. So I've got this delta s e to the negative delta times t minus t minus k r e to the negative r t minus t. All right. Now it's interesting if you looked at the formula sheet, you see that kind of thing in there. Delta s e to the negative delta t minus t minus rk e to the negative rt minus t, and then minus this thing over here. So really what they're saying is, so this is actually all the theta for the call. And if I wanted the theta for the put, I could kind of take this over here, move this over there, and then I would actually have all of that minus all of this. All that's going to kind of go away. So I'm going to have all of this, and it turns out that what's going to happen is we're just going to get the theta for the call plus all those things here. And we kind of knew that anyway. We sort of could have solved that, right? If I wanted to know theta for the put, I can move this over and take this. But down here, notice how they're like reversed. But that makes sense because I am subtracting them to that side, right? So, but that's how they got it. But it's interesting that those terms are sort of even in the original formula for the theta for the call. But this one is one where you couldn't really derive it by hand. It's too complicated. You'd have all that plus this big, ugly, nasty thing here too. And it's just like, oh, so that's why they give you the formula for it. And if you wanted the delta for theta for the put, you could just get it from the call first and then, put this in there. Okay. All right. Now, interesting with this is the only option that's a little bit weird as far as what its values could be. We saw that for the gamma, they're always positive for both. For delta, call was positive, put was negative. But this one is, well, it's usually negative, but there's kind of some weird cases for both, like some just kind of strange situations where it could end up being positive, but they're usually negative. And you can kind of think of that where, yeah, as you get closer to expiration, the options will sort of devalue. They're not going to be as valuable because you're kind of getting closer and you're knowing more information. So there's not as much uncertainty. So there's not as much to like charge for, so they call that the decay of the option. And as you think about this, by the way, you kind of assume everything else is staying the same. So if you're just looking at the derivative with respect to little t, that's it. It's just kind of like thinking everything else equal. What happens as I move closer, and as I move closer, it should generally like sort of like lose value a little bit, decay as you reach expiration. Okay. All right, and then one other thing on this slide that's super important is what they call the delta gamma theta approximation. So the delta gamma theta approximation is really nice because it's actually got all the big three, right? The delta, the gamma, and the theta. But the approximation is actually pretty reasonable if it like to memorize as a formula, because it says that the change in the option price, dV, is about the same as, okay, well, delta ds, 1/2 gamma ds squared plus theta dt. Now, these aren't really that crazy of a combination of things to do. Because, for example, we know that delta is dv over ds, right? So I'm going to write that, dv over ds. And then they said to multiply it by ds. But notice how that's exactly the denominator there. So it's kind of cool. They sort of like cancel out. And then plus 1/2 gamma. So gamma was the second derivative, d2v ds squared. And then what do you multiply it by? Well, ds squared. That's interesting. Ds squared. So that's going to kind of cancel also. And then you got theta, which is dv compared to d little t. And then what do you multiply by? Dt. So that kind of cancels. So really, like, all of these are kind of giving you, I mean, this isn't really what you're doing, but just to help you kind of remember the formula, they're all sort of telling you how much the option is changing now for different reasons, but they're all kind of telling you like, oh, each one of these is going to contribute some change to the option price. And then the middle one is a little bit of a weird one because of this 1/2, but it actually goes back to like Taylor series. Remember for Taylor series, when you do like the derivative, you divide by like whatever derivative it was factorial, like you did do like the second derivative at a certain point over 2 factorial and then times the, that term. Or if it was the third derivative, you'd have to divide by 3 factorial. So that's really what you're doing, is you're dividing by 2 factorial just to fit because it's the second derivative, right? That's what's happening. Actually, this is a multiple variable Taylor series. That's what this approximation is, and it's just picking the first couple of terms, the ones that are the most important, and that's why it's an approximation and not exactly equal, because of that. Okay. But all of this kind of gives us an idea about like, oh, the change in the option price. So if they wanted like, what is the new price, you'd probably have to find the change first of all, and then add it to the current one, right? So they could ask you 2 different questions, but just as long as you know what the delta gamma theta approximation is, it's all giving you just kind of what you think that the option will change by. And it's related to the Greeks, those first 3 Greeks we talked about. Okay, so with these 3 in mind, let's just do a problem here that kind of helps us with the delta gamma theta approximation. I just want you to understand it. And then, a lot of times they make this kind of big issue about theta. So, because they usually say it's like, oh, theta is daily. And that is true. It usually is in practice, it's daily. This formula, however, is really annual because time is always measured in years, really. So if they wanted to know like, oh, okay, if they actually wanted a day's worth, and these are like daily thetas or whatever, then I would just have to divide this by 365, because this tells me the change per, without 365, that's the change per year. So if I wanted per day, it's just 1/65 of it. Okay, but it's just because in practice, like kind of after a day, everything all changes anyway. So they don't want to give you the annual, and then you kind of just want to know like, okay, tomorrow, how much am I going to expect this thing to change by? That's kind of the more practically important thing for you if you see these values. Okay, but the equation itself is annual. Like all the t's that we ever use are always annual, right? If we want a month, we have to do 1/12, like it's just always how we are. but sometimes they can give it to you different. But just so that you know that, then you can adjust accordingly. Okay, so we'll see that here. They actually give us here weekly theta, so one for a week. So I tried to do one where it wasn't daily and it wasn't annual, so we could just kind of see how we would adjust that. Okay, but all right, so let's do this one here. So an investor purchases an at the money 6-month 50 strike straddle on the stock, paying 1%, continuous dividends, and the straddle costs $5.60. Okay, straddle. Do you remember what that one looks like? It's a 50 strike straddle. And for me, straddle, I thought about like, oh, okay, it's kind of like straddling the fence. Those are like the 2 feet, 2 legs. So this one is the V. So, but if they purchase it, it's the V that looks like that. No problem. And the cost or value of it is $5.60. Now, do you remember what the portfolio was? How did you comprise this? So go ahead and write it down in your paper and we'll see if we're right. How did we comprise this? Did we go long or short, or what did we do? And if you said plus a call plus a put, you're totally right. Great job. Because the call is going to contribute this part of it. It's going to be 0 before and then like upward slope after. So that's a long call. And then a long put will be this one, where it goes down and over. And actually where the other one is 0, that's where the other option kind of gets its action. And so we get that the sum of those 2 things is actually exactly this straddle. Okay. Okay, so this is what we know our portfolio is going to really consist of a call plus a put. Okay, no problem. Both at strikes 50, which is nice. So in the table below are the values for several Greeks for a 6-month 50 strike put. Okay, so these are for a put. I'll just kind of write that down here. Those are the put values. The risk-free rate is 4% and stock price in 3 days drops to $48. Determine the approximate value of the straddle. Okay, well, this sounds like, since they give me delta, gamma, and theta, they didn't even tell me to use the delta, gamma, theta approximation, but that's the only thing that I actually have dealing with these to help me to see how much the price actually changes by. So they don't have to say to use it, but we know to use it because of what they've given us. I think they might sometimes tell you to use it, but I don't think they have to. So just keep that in mind, but we're discerning, oh, delta, gamma, theta, that should be kind of the first thing I think of anyway, this delta, gamma, theta approximation, and see what we could do. Okay, so what do we know? Well, I guess if I'm going to do this, I need to know the delta, gamma, and theta, not just for the put, but for the portfolio, because I want to know how much the portfolio is going to change by. So I've got here, my portfolio is C plus P. Now here's the beautiful part about the Greeks. The Greeks are actually really nice because if I'm adding things, doing the derivatives like we saw before is like super nice. The derivatives will just, I'll be able to just do the derivative each one in turn. So if I wanted to know delta portfolio, I'm basically doing the derivative of this with respect to S. So it's actually delta call plus delta P. Right, that's it. So the Greeks are actually super nice when it comes to doing these like combinations and portfolios. Oh, I could just kind of make it like that. So it's beautiful. Now I need to know the delta for the call because I know the delta for the put is minus 0.43, so no problem. I could, if I want, I could try to like, it's going to be kind of a pain, but I've seen some people do this where they'll say, okay, this is negative 0.43, and then they try to solve for, they kind of discount by this, they solve for n of negative D1, find that, put it into D1, and get the delta for the call that way. And you could do that totally fine, but we're going to do it realizing that, oh yeah, we can actually just leverage the power of put call parity to tell me what one thing is if I know what the other is. So we're going to kind of get a little slicker. And it's actually real quick to do. If you don't memorize it, that's okay. Call minus put is SE to the negative delta T minus KE to the negative RT. This one doesn't matter about the time thing. So I could just do the derivative nice. So delta call minus delta P. I'm taking the derivative with respect to stock price now. So delta call minus delta P equals, okay, derivative of the first thing with respect to S is just e to the negative delta times time. So the nice thing is if I wanted delta for the call, it's just going to be delta put plus e to the negative delta T. Awesome. And great. So actually I know delta P is this negative 0.43. Awesome. And I know my little delta is what they say 1% dividends. So I know that this is going to be negative 0.43 plus e to the negative 0.01, and it's for 6 months, so I'm going to be over 2. So that's delta call, but I'm going to add that to delta put anyway, so I'm going to actually have to add another delta put in there. So let me see if you get the same thing, but I'm going to have like a negative 0.43 twice now, I guess, right? So negative 0.43 plus e to the negative 0.01 over 2. And then minus another 0.43. So I got 0.135, whatever. I'm going to store that into X so that I don't have to find it again. But it's easy to see on my paper. So just timing wise and just clutter on your brain and everything, I think it's all important. Okay, so now let's find the gamma for the portfolio. Gamma portfolio is, well, again, it's the Greek, so I can just go, this is just gamma call plus gamma put. I'm really doing the second derivative of this with respect to stock price twice, but because it's just a sum, derivatives work out super nice. But in this case, remember if we wanted to go back to our formula or something, we actually saw that these were equal. The gamma for the put equals the gamma for the call. So this is really just going to be 2 times 0.06, which I could do on my calculator. So, well, it's 0.12. I think that's easy enough. I'm not going to really type, I'm not going to store that. You could, if you want, store it into Y, that's fine, but it worked out clean enough. Might as well just type it in. And now the theta. So the theta for the portfolio. And because they gave me weekly theta, I think I'll find the weekly theta for the portfolio. Okay. So I'll just call it like W theta, right? Weekly, however you want to denote it. But you can go like that, but that's okay. I'm just basically going to be taking the derivative of both of those. So it's going to be the weekly theta for the call plus the weekly theta for the put. Easy enough. Oops. Weekly theta for the put. The weekly theta for the put I've got is a negative 0.04. So I just need to know what's the one for the call. And here I can't actually set this equal to, like they said theta for the put was equal to, what was it, negative 0.04. So I can't really set this equal to negative 0.04 and then try to solve for call or something. I can't really, well, I guess I probably could actually probably solve for theta. This is actually what we're going to do. It's interesting. But yeah, here, yeah, actually we have all these things. So you can go straight to this formula if you want, but we're going to have to be a little bit careful because we're talking about weekly. So yeah, so why don't we actually just use that? It's the same thing as if you were to take the derivative, you'd have to use the T minus T version though, like if you took the derivative. But what they said on the previous page, theta put equals theta call plus RK e to the negative, so RK e to the negative R times time minus delta S e to the negative delta times time. You know, that's easier. I was going to do the derivative of the put call parity, but might as well use what's there, right? So, all right, so this is it. Now, the thing is, this is per year. So I've got 2 options. I could kind of actually do annual theta or for the portfolio and stuff. I could do that and then scale these, which is fine. Or the other thing is I can just kind of remember that, well, back here, this is annual. So if I wanted to do like daily, I would have to divide this. If these were actually daily thetas, I just have to divide by 365. If it's weekly, I just divide by 52. So I'm actually gonna divide this by 52 to get weekly theta, called weekly theta for the weekly thetas. And then we have a question too. It says, if the problem didn't specify that the theta was weekly, would we assume it is based on the option term, t equals a half? Not necessarily. Yeah, if they didn't say it was weekly, boy, I think they'd have to be. I think if it was me, I would assume it was annual. But sometimes I think, I don't know if they're able to just say theta and you assume that it's daily. I guess I would think of like which one might make more sense with the number. Like if it's a pretty big number, then it's probably a whole year's worth. But if it's a pretty tiny number, it's probably like a day's worth. So, yeah, I'm not sure. Yeah. And then question 2, do we have to scale the interest rate and dividend rate to? Oh, okay, well, so these are always still time up here. But yeah, these would be, if I just wanted weekly thetas, I would have to divide this whole term by 52. So we won't actually have to like divide that by 52 and that by 52. It's not that complicated as long as I'm consistent, and you'll see that. Because the R really is still an annual R, and the delta is still an annual delta. Those are still annual rates. So that's why I'd keep those the way they are. Okay, yeah, good question. So the nice thing is, okay, if I wanted the weekly theta for the call, okay, well, weekly, so I guess I could kind of take the weekly theta for the put and subtract all this stuff off. So let me do that. Weekly theta call equals weekly theta put minus this big old monster here. And let me kind of plug in the values there. So I'm going to get negative 0.04 from the theta for the call, or sorry, for the theta for the put. And then minus, and then I'm going to actually use the N over D button. So just on here, N over D, so I know I'm subtracting this whole big fraction. I'm just going to do this whole fraction the way I see it here. So R 0.04 times K, and they said 50 strikes, so 50 times e to the negative 0.04 over 2, 6 months, minus delta 0.01 times S. Well, they didn't tell us S, but they did say it was at the money. So I guess current stock price S is 50 also. So 50 e to the negative 0.01 over 2. And all that's going to be divided by 52. Okay, so I got like a negative 0.068. So that's this number, negative 0.068, whatever. But then I'm going to also, so that was just the theta for the call now. But I still need to add the theta for the put. So I have to also subtract another 0.04. So I'm going to minus 0.04. So I got negative 0.1081, whatever. I'll store that into Y. Okay. Questions about that? Any questions about that one? So just keeping it straight. That's all we're doing. We're just kind of doing both separate. It kind of would have been nicer if they would have, if my portfolio was like call minus put, that would have been even nicer. In fact, they might do stuff like that. Maybe call minus puts. And so then maybe you won't even need to compute any of the options. You can just kind of compute the derivatives of the right side of put call parity. Like I feel like that would be kind of a cool gimmick on a problem, but now we'll see. All right, so now we go back to the delta gamma theta approximation. And from there, okay, well, it says the change in the portfolio now is approximately delta portfolio. And we think of delta, the denominator is ds. So I'm going to have to multiply this by ds plus the gamma, which was a second derivative. So that's why I've got that over 2 factorial. So gamma portfolio. And then that had a ds squared in the bottom. So I'm going to have to multiply this by ds squared. And then plus the theta for the portfolio times dt. Okay, and I can use the weekly theta in there as long as I'm consistent now. Okay, so let me see what I got. So this is, okay, delta for the portfolio, that was X. And then DS is just change in stock price. So what was the change in stock price here? Okay, so it was originally at 50, but then it drops to 48. So I guess the change would be -2. So cool, so DS is -2 plus 1/2. The gamma was just that 0.12, easy enough. And then DS squared, so -2 squared. And then the theta for the portfolio, that was what we stored into Y, but it was the weekly theta. So I need to multiply it by weeks. So they said at the stock price in 3 days. So because it's a weekly theta, I just need to be compatible. Like how many weeks worth did I want there? And I actually want 3/7. So it might be a little bit strange, but because the theta is like weekly, I would just need to keep compatible. So if it was daily, I could multiply this by 3 because it's 3 days worth. But if it was annual, I'd have to multiply by 3 over 365 because it's, annual. So I'd need to scale it accordingly. So just make sure that you're kind of consistent with it. That's all you need to do. Okay, it doesn't have to be harder than that. This one a week is kind of a little weird, so that's why I wanted to put it on here, but that's it. All right, so let's see what we get. So X times -2 plus 1/2 times 0.12 times 4 plus Y times 3/7. And for this, I got -0.076 some stuff, so -8 cents maybe. So in other words, this says that the portfolio here will change by -8 cents. So the portfolio will decrease by 8 cents. Now, what did they ask for? They asked for the approximate value of the straddle. So they want to know how much is the straddle going to be worth. So you're like, oh, okay. So the new value is, well, it used to be 560, and now it's going to drop by 8 cents. So minus 0.08. And this gives us, 552 about. So just keep in mind that the delta gamma theta approximation doesn't give you the new price. It tells you how much the price will change. And that's kind of consistent with sort of how we multiply stuff, and it's kind of in the formula itself anyway. So, okay, but any questions about this one? Okay. All right, great, yeah. And if you wanted, you could have like scaled this. I think you could have multiplied it by 52 to get annual theta if you just kind of wanted to keep it all in annual. Or if you want to go daily, you could have divided by 7, if that's kind of what you're more comfortable with. It's like, yeah, feel free. But as long as you understand what you're doing, I think it makes it easier. So. All right, now just wanted to talk about just briefly these other 3 Greeks. They don't come up as much, but just kind of some things where we can remember it by. But Vega is volatility. It's not actually a Greek letter, so I don't know, it just sounds Greek. So I don't know why they did that. But Vega, V for volatility. So we're actually going to take the derivative of the option with respect to sigma, so the volatility. And if I wanted, I could do here the derivative with respect to volatility here. But interestingly, on the right-hand side, we don't see volatility anywhere. So the whole right-hand side is 0, which means that the Vega for call minus Vega for put equals 0. So they're equals. Vega call equals Vega put. So that's nice. And actually on the formula sheet, it just says Vega for call and Vega for the put are both this. So that's nice. And we can also tell that they're greater than 0, right? Because it's positive, 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 positive. Everything there is positive. So this is a big positive quantity. And so we can actually tell without really knowing anything, just from the formula, that the Vega is always positive for both. So what does that mean? I think this is kind of an interesting thing. So as volatility increases, the option increases. right? If Vega was negative, then for the volatility increasing, the price would go down. But the more volatility, the more expensive an option is. That's kind of insightful if you think about it. And it actually can help us with a question that they sometimes ask about comparing the price of an Asian option with a regular option. So here's a chance to vote again. Okay, so what about a regular call with a certain strike as compared to an Asian call where so maybe I'll say here SKT. But what if I took the average price instead, kept the same strike, same time? Which of these do you think would be more expensive? So we'll say yes for this, no for this one. Which one do you think is going to be more expensive? And let's take a think about it. Which one do you think is more expensive? The Asian one or the regular ordinary call? And same thing for put, it wouldn't matter here actually. Okay, so we got some good answers here. Okay, good. So we're talking about volatility. So this would be kind of the issue here. Which of these, a regular stock price or an average stock price, is more volatile? Or you could say which one is more consistent, which would be less volatile. And you might think like, oh yeah, if I average out a bunch of stuff, that value is going to be more consistent, right? If you're talking about like, oh, just a single person's weight versus like the average of 100 people's weights, like if you average out 100 people, yeah, you have some bigger ones, some smaller ones, but they're going to kind of average out, and it's going to be more, the values are going to be kind of more consistent. So here, this actually has less volatility. And so the Vega actually helps us to know how to answer this question, because it says, oh, as volatility increases, the price increases. So as volatility decreases, the price decreases. Actually, the regular call is going to be more expensive than an Asian call, well, an Asian average price call, not average strike. So that would be a different story. But because it's less volatile, the price goes down. So sometimes they might kind of ask you that. It would just have to be less than an ordinary call. Okay. So thanks for voting. Appreciate that. Okay, good. So it's kind of insightful. It's like, oh, okay, that's kind of nice. And that sort of makes sense too, because if the item under question, the uncertainty of it, if it's like all over the place, then it's like, man, you have to really guard yourself against a lot of craziness happening. You'd actually have to charge a lot for that thing, or it would cost a lot, because it's like its potential to pay is actually pretty big too. But if the values aren't really that crazy, if they're pretty consistent, then it's like, a call wouldn't really be like that valuable. Okay, so you can think about it that way too if you want. All right, rho and psi then, these are just the last couple here. So rho is with R, even though it looks like a P. So this is with a rho. So this is, so that's the derivative with respect to R. And the psi is then with respect to the last thing, is the only one that kind of doesn't really work well, but that's with respect to the dividend rate. But as you can imagine, these two would sort of behave opposite. And we actually see that from the formulas. Here's from the formulas, we can tell that the rho for the call is positive and the rho for the put is negative. But then down here, the psi for the call is negative, but the psi for the put is positive. So they're going to behave opposite, but it kind of makes sense that they would, that they'd be like that. And then we can, but we sort of get those for free here just by looking at the formulas. We know from the formulas. If we forget, we can get it from there. And if I wanted to do the put call parity, I could do the derivative with respect to R with these. So I'd have rho call minus rho put equals. All right, the derivative here, well, with respect to R, there's nothing. So that's just a big zero. minus, okay, well, ke to the negative r, so the r is in the exponent of an e, so I'm just going to copy the whole thing down, ke to the negative r times time. And now the derivative of the exponent with respect to r. And what would be the derivative with respect to r? Well, I guess it's negative r times time, so I guess I would just kind of, the r would sort of go away, right? And I'd have negative t minus t. So I'd actually have positive t minus little t here. And that would be the difference between row call and row put. And again, not really clear from these formulas, but it is true that their difference is just going to be t minus t, ke to the negative r times t minus t. Or you could just say time times ke to the negative r times time. It's fine. And then for the volatility, or sorry, for the dividends, so derivative with respect to delta of this, same sort of thing. Psi call minus psi put is, okay, derivative of this thing. And okay, since the delta is up in the top, I'm just going to take the derivative, just going to copy it down, se to the negative delta times time, but then times the derivative of all that with respect to delta, which is negative t minus t. And then the derivative of this part is just a 0. So we can see if they give us 1, we can get the other pretty easy. Okay. Oh, and then, so we had a question, I think back to here again, about these, how do we compare them? So just one last, kind of just again, the answer is related to the volatility. And so we just want to know which values are more spread out, the average of a bunch of samples or just a single value. And we kind of remember back from statistics class that if I took the average of a bunch of values versus just a single value, the average would be much more consistent. And in fact, that's why we kind of like averages. It's sort of, it helps us to, like, we're not just looking at a single value and trying to make all these inferences based off a single value. An average of a bunch of values would be much better for me because that gives me a much better idea about it. So yeah, so that just means that the average price instead of a single price would be just less volatile. That's kind of how you translate that. So, but yeah, great. Yeah, thanks. Good question though. All right, one last topic here. Now, this isn't really this is kind of an anomaly here with the Greeks. Even though it is actually a Greek letter, it doesn't behave like the other Greeks, especially when it comes to like portfolios. Okay, so the formula here that we want to remember is actually delta S over V. Now, it might seem weird though, because it's a percentage change in V over percentage change in S. So it's almost like you'd expect the stuff with V's up on the top and the S's on the bottom. But it actually doesn't work that way because, well, it's a percentage change in option. So we're really talking about how, well, it's actually how the option changes compared to its current price over the change in stock compared to current stock price. That's really what's happening here. Okay, so that's what I mean by percentage change. Oh, how much does it change by compared to how much it is? So that's change of V. But if I think about this, okay, divide by a fraction means multiplied by the reciprocal. So I've got dV over V times the reciprocal of the other, S over ds. And that's where I get, oh, okay, dV ds, that's just delta times S over V. So I get that right there. So this is actually the legal definition of it, but it turns out that this is sort of a lot nicer for us to work with. So this is one where it is something to memorize. Like I said, I'm not a big memorizer, but comes up a lot. But actually it isn't so bad. And usually it's a call or put or something. So this is just the call or the put price, but it could be a portfolio where it would just be the value of the portfolio, how much it currently costs. Like that's how much it would, that's what we mean by value of that thing. Oh, then we got a question here too about, is the delta from the replicating portfolio that we did with the seminar 3, is that related to the delta for the Greeks? And yeah, actually, remember back with that one, the delta was e to the negative delta, h times, well, value in the up minus value in the down over stock in the up minus stock in the down. But isn't this really just like change in V over change in S? Exactly the same. Yeah. And you might think of that with like the whole delta S plus B, which is kind of interesting. That's actually where these come from, because with a call, remember, a call is actually like, so I'd have delta S over, so if it was for a call, it would be delta S plus B with the replicating portfolio. With a call, the delta is positive and the B is negative. So it actually kind of looks like that, sort of. Right? And then for a call, then I definitely know that the top is larger than the bottom, and both are positive. So that's why a call is actually greater than 1, because the numerator here is actually larger than the denominator. So you don't really need to know that too much, but it is actually, yeah, you start seeing a lot of symmetry with all this stuff, right? That's great. The other thing I wanted to mention is that, oh, well, I'll get back to it in a minute. So sorry. But yeah, perfect. Yeah, great. So back with the delta for the replicating portfolio. Yeah, it follows the same kind of pattern. It's just change in option compared to change in price. Beautiful. Yeah, great connection. Good job. It also has this little extra e to the negative delta H thing, but close enough. At least we kind of see the pattern here. Okay. Some of the properties, okay, so, well, first of all, because the stock price is always positive and the option, it's always the option price, if it's for a call or a put, that's always positive. Then the sign is going to be dictated by the sign of the delta. And we saw that for calls, it was positive, and puts, it was negative. So we actually have the omega for call is positive and omega for put is negative. So we see that, that's okay. So you can have this being negative, totally fine. With calls, it turns out you can actually say it's not just positive, but more than 1. So, okay, but whatever, no problem. I don't think that's really a huge deal, but the properties, here's why we care about it. The properties. It allows us to relate certain features about the stock to those same features about the option. So like, for example, for a call, it could tell us, it actually tells us the volatility of the call option or a put option based on the volatility of the stock and omega. So here's where it kind of gets this idea about elastic. It's sort of like, it's sort of stretchy, right? It kind of tells us like, oh, we know that the stock has a certain volatility, we need to stretch it by that factor to get the volatility of the option. And because it could be positive or negative, we need to put absolute value around it this time, right? Because volatility is always positive, it's always just spread, that's all they mean. Okay, and then there's another thing that stretches also, and that is actually the kind of the, what do they call this? The, I forgot what they said, what they call this, the rate of, sorry, it's just escaping me right now. If you remember it, just shoot it to me. So not appreciation, it's not the rate of appreciation. A rate of appreciation would be alpha minus delta. Oh, the risk premium, that's what it was. So the risk premium, in other words, like how much above the risk-free rate am I getting? Because remember how we're like, oh, everybody should be able to get risk-free rate. So if you're getting risk-free rate, that's like nothing special. We really want to measure how much above the risk-free rate we're getting. That's the thing that's really the important part for us. So that's why both of these have like, oh, how much above the risk-free rate am I actually dealing with? And it turns out like that value stretches by the same factor, but it could stretch negative, which is weird, but it could actually become in a negative direction, but that's okay. It's no problem. It could happen. Okay, now here's the thing that I wanted to kind of link here. This actually relates to CAPM. So we're not going to talk about CAPM in this seminar series, but CAPM actually, this is almost the formula for CAPM if this was beta and this was like expected return on the market, and this was the risk-free rate, which it is here, the rate, like the regular rate. And then this is, well, if I move the minus R over to the other side, so I could say risk-free rate plus beta, and then this would be like, you know, the expected return on a certain asset, something like that. It actually has the same exact form. And it actually, beta is almost defined in exactly the same way. Remember, it was like percentage change in the stock compared to percentage change in the market. Remember that? Like that's what beta was defined as. So beta has this sort of like same sort of feel that we have for this. And it is this idea where it's like, oh yeah, beta will kind of like stretch the market excess return, you know, to whatever your excess return is, or risk premium, they also call it that too. So if you have like a beta of a 2, that means like, oh, your stock is going to like react twice as much as the market would. So if the market is kind of like expected to gain 5% over the risk-free rate, then your stock will kind of like double that. It'll be like 10% above the risk-free rate. And that's actually what they're saying here. It's going to be the risk-free rate plus beta times, well, stretch it by whatever factor times the excess, you know, risk, excess return for the market. That's exactly what they're doing here. Okay, so just kind of a connection for what it's worth. And they also kind of talk about the Sharpe ratio too. So the Sharpe ratio is interesting because, so the Sharpe ratio, we remember, was just basically the expected return minus the risk-free rate over the volatility. So that's what it was for a stock. So we'll say Sharpe ratio for a stock. They do have a letter for that, but we'll just kind of use the SR just for us. And then the Sharpe ratio for the option would be just gamma minus R over the volatility for the option. And by the way, that's the letter here. It's just the little gamma. We saw capital gamma is this one. That's the capital G in Greek. Here's the little g in Greek. It's the little gamma. We've seen that before too, by the way. That's the capital delta, and this is the little delta, capital D, little d in Greek. So that's why we're like, wait, do I say two things are delta? Yeah, I do. Yeah, we do sometimes. But this, the interesting thing here is that this is kind of, this is actually, it's an expected return on the option. So I'm just going to put that here, expected return on the option, the V, on option V. But it's sometimes they specify it, it's not the average over a long period of time, but the elasticity is always kind of like right at an instant, right at the current instant. And the reason for that is because, well, over a period of time, all these things are like in flux. The stock price is in flux, the delta is in flux, even the option price is in flux. All those are kind of changing all the time. So it's really only valid like kind of right now. So that's why they might call it the instantaneous rate of return on an option if we're using this relationship right here, because omega is like in 5 minutes from now, it doesn't necessarily have to be related much to what it is right now. Even an instant from now, like things can change so fast. So they might just say, oh, it's an instantaneous return. So back to the Sharpe ratio, kind of the neat thing is that I would really just need to divide this by sigma S, and I need to divide this by sigma V, but I actually have that equation that relates those two there. I can actually divide this by absolute omega S over here, right? I can actually just divide the left side by sigma V, the right side by absolute omega, sigma S, and I get the Sharpe ratio for V equals, well, omega over absolute value of omega. So whatever the magnitude is goes away, but the sign will still be preserved. So if omega is positive, then this will be positive. If omega is negative, then it's just going to be a negative one. So I'm going to get plus or minus the Sharpe ratio for the stock. Okay, so interesting that even though the volatility and everything changes for an option, the Sharpe ratio is either the same or negative. So for what it's worth, I just wanted to kind of put that there so we could see it. Now, okay, well, so one last problem, then we'll take a little break here. So one last problem. So we, oh, and then here I kind of added instantaneous. Sometimes they'll put it there, sometimes they won't. So I figured probably just put it there just to be safe. But this would be actually a very computationally intensive problem, but I tried to save us some time and work by kind of doing some of the computations for us. So just that we don't have to spend so much time on that here. So, all right, but anyway, so the price of a stock is log normally distributed, or they could have said, assume the Black-Scholes framework, totally fine. So for the stock, current price is 55, they give us all the stats. Okay, no problem. And then a portfolio consists of 2 long 3-year 60 strike calls and 3 short 3-year 60 strike puts. Okay, so it's like they're both 3 years, both 60 strike. Since the strike's not really changing, I mean, I'll just kind of write my portfolio real simply as I'm long 2 calls and minus 3 puts. I could be more specific. I could say put at 60, or I could say put stock 63, 60 comma 3. I could kind of use the real verbose one, but I think this is good enough. I mean, that captures what I really need out of all this. Then it says determine the rate of return of this portfolio, or the instantaneous rate of return of this portfolio. So for that, if they were to say that, we're like, okay, rate of return of a portfolio. Oh yeah, that would have to be that whole gamma thing. And you're like, oh, okay, so I'd want gamma minus R is omega for the portfolio times alpha minus R. And it's funny, out of all this, I pretty much have everything except omega, right? And the thing I'm looking for. So I have alpha, it's 0.15. I've got R is 0.04. If I find omega, then I'm good to go. So here's where it's not going to behave like the Greeks. I would love it if this was the case, that omega for the portfolio was just 2 omega calls minus 3 omega puts, but that's actually not the case. So this is where it's going to differ from the typical thing that the Greeks do. And it's just because, well, I'm really taking the derivative. Oh, I wonder what happened here. So delta S over V. So it's really because I'm taking the derivative of this with respect to, like, I'm trying to like kind of do this kind of thing. And it's just like, it got weird. I got deltas here, I got call prices, and it's like, it's not like I'm really doing some simple derivative thing here. So, but it's okay. We can handle this a couple of ways. There is actually a way that I could say something about omega for the calls and something for omega for puts. I can do this, but it's going to be some sort of weird weight out in the front. And it's not really that complicated, but it's just going to be like a weight, like when you do with the stocks, where it's just going to be like, oh, price for that thing compared to total price, or like cost or amount spent in that thing compared to the total amount spent for the whole portfolio. So you could do that here. But I'll show you kind of like an easier way that I think works good. But you could, it's actually just like, you know, total for the calls over the total for the portfolio, the cost. And then this would be like the total for the puts over the total for the portfolios. Oops, I say that, huh? So it's kind of like the weights that you do in the capital markets stuff. So, and you can do that, that's no problem. But we're going to actually go back to the whole idea where it's just like, oh, it's just delta S over V. So it's actually delta portfolio S over the portfolio, the cost of the portfolio. So it's like super nice. So if I wanted to do the omega for the portfolio, this is what it is. And now this goes back to, okay, well, I'll need the delta for the portfolio. I'll need the cost of the portfolio, and then I'll need the current stock price, but I kind of got all that stuff. So, so let's kind of do that. So let's find, first of all, delta for the portfolio. That I can do as the Greeks. It's going to be plus 2 delta puts minus 3 delta, oh, sorry, plus 2 delta calls minus 3 delta puts. Easy. That stuff. Those Greeks actually work great with these portfolio sums. No problem. And so then here you would actually need to go into Black-Scholes, compute out, the D1, the D2. You'd have to find out the delta for the call, delta for the put, using the formulas that we have earlier with the N of D1s and all that. But I kind of did all that for us, so we wouldn't have to, and I just rounded, so this won't be a great answer. But you can go back into Black-Scholes to get the real answers if you want all the decimal places. But for us, I just kind of wanted to illustrate this kind of point, and they will definitely have no problems asking you to do this. Go into Black-Scholes, find the call, the put, the delta for call, delta for the put. It's a ton of stuff to do. It's all kind of the same D1 and D2 though, so it's not like horrible, but yeah, it's going to be, it's just kind of a lot of computations. And to do it in 5-6 minutes is like not that easy, but. All right, so when I do this out here, so I'll just use the answers that they gave me just to be quick about it. So 2 times 0.46 minus 3 times negative 0.45. And I got 2.27. And then I can also get the portfolio here, basically the cost. That's really what we want. So it's going to be plus 2, however much a call costs. So I'll just put here cost or value, kind of the same thing, minus 3 times the amount that a call, or the account for a put. So kind of just going back to what we normally did. Just want to know how much this thing's worth, which is the cost. If it's worth 20, it's going to cost me 20, right? So not cash flow. Interestingly, it kind of almost feels like it should more be a cash flow, but it would actually be negative cash flow. So, okay, but it's okay. Just remember, it's just the cost of whatever it is. So then, okay, how much was the call and the put? Well, again, Black-Scholes, I did it already, but we could just put those in there, 574 and 868. And here we get something that may be a little bit surprising to us, but so 2 times 574 minus 3 times 868, got negative 1456. So we're like, ooh, negative, is that kind of bad? And it's like, not really, it's fine. But I just kind of put it in here like this. So just make sure to kind of put it in there. So I've got the delta for the portfolio is the 227. The current stock price, which was, okay, they said it was 55. And the value, which was negative 1456. And you put it in exactly as negative. That's why it's nice to kind of have like, oh, cost tells me value, how much it would be. And all this, if I compute it out, so 227 times 55 over negative 1456. And I got negative 8.57486. I'll store that into X. So I don't have to get that again, but that's it. Okay. And then, yeah, now that I got that, great. I'm just going to kind of think back up to here and I'll just kind of fill those in. So I'm just going to kind of do that now. Gamma minus 0.04 is omega X times 0.15 minus 0.04. And I could solve for gamma. And I got negative 0.90323. Okay, great. So that's negative 90%. So pretty bad. Sometimes you get some pretty really crazy, awful things here, but it's okay. You could get like more than 100%. You can get, you can get all that. So if you get some kind of absurd answers, you might not be wrong. Okay. But yeah, I just kind of want to show you how I would work with omega if it was for some sort of combination of assets. That's fine. You could just kind of just go back to that the delta is the easy thing to work with. And I feel like that's the easiest way to go with all these. You could do the weights, but that just, I don't know, just to me, that seems more complicated. What that would be here, by the way, would be the weights would be, I guess I would do 2 calls. That would be the weight. So this would be like 2 times 574, because that's how much I'm spending for the calls, compared to the total value of the portfolio, which was actually this negative 14 number. So I'd say that divided by that negative 1456, that would be the weight. And then for the puts, it would be negative 3 times 868 compared to negative 1456. But then I'd have to compute the omega for the call, omega for the put anyway. So I'd have to do those with delta S over B, like over C, or delta S over P, compute those out. I'd have to use these things to compute those anyway. So you see how it's kind of like, yeah, it's also pretty complicated. So, so I feel like this is just the simplest way to go. Just go back to that. All right, so okay, so let's take a break here for a couple minutes. We'll come on back and then we'll just finish off here. We've got some delta hedging, and then I just wanted to talk about some exotic options when we get back. Okay. All right, so yeah, just kind of a little bit about elasticity. It does feel like it's related to the beta from the CAPM stuff. Yep, same exact idea. Just this one's for like puts and calls and stuff instead of like stocks, but yeah, same basic relationship. Now, now I just wanted to talk about hedging, so like delta hedging specifically. And I think I have like maybe 3 problems on here, but one's where delta hedging could be kind of a complicated process, and it's sort of hard to keep track. Like, am I long, am I short? But the portfolio thing is going to really save us here again, especially because we see how the Greeks work super easy with portfolios, all except for the omega, but it's not really considered a Greek anyway. So, but okay, so at any rate, so if we want to hedge these things, so, well, if my portfolio looks like this, I'm long in something, and then plus a certain number of shares of stock, and then I've got plus a certain number of shares or a certain number of like plus N delta stock plus M delta V. Said back at the beginning, what was the delta for a stock? And you think like, oh, delta for a stock, that's change in stock compared to change in stock. Oh, that's just a 1. So this thing here is just going to be a 1. Sorry, it looks like it's kind of lagging a little bit here. I don't know why. Sorry about that. But the middle term there next to the N says delta S. Well, it's actually going to be, it's going to be a 1. Good. And then I could do, okay, yeah, hold on one sec. Yeah, I felt like it was having a bit of a hard time here. Oops. All right. Okay, all right. I feel like that's better now. Okay, but at any rate, okay, so next to the, okay, so N, so the delta for a stock, all the way back to the beginning. So what we did all the way back on page 2 was that the delta for the stock is 1. Okay, so and that makes sense. Yeah, we saw that is just change in stock compared to change in stock, which is, yeah, it's $1. All right, so now, and then for like the gamma for a portfolio, so again, just kind of like just a different Greek, but actually it's just going to be the gamma for the first thing plus N gammas for the stock plus M gammas for the other option. I mean, really, it's just like kind of how we did it. We're just going to, portfolio tells us everything. In this case, though, actually, the cool part is that this is actually every Greek apart from delta for a stock is actually 0, which is nice. Now, that's not all that easy to see, but it would be like, let's say here, if I wanted to do the gamma for a stock, right? So what that would look like is, well, it's going to be the derivative of the delta for the stock compared to current stock price. But we saw that delta for the stock was 1. So it's kind of like the derivative of 1 with respect to S, but it's constant, right? So that's just a 0. So the gamma for a stock is actually 0. And actually theta 2, we could think of this theta is, well, it's going to be the theta for the first option plus n thetas for the stock plus m thetas for the other option. But then the theta for a stock, what would that look like? Well, theta for the stock is change in stock compared to change in time. But there's really no way for us to know how the stock is changing in time. It's not like some formula we could just take the derivative of or whatever. So this actually also is just a 0. Especially because remember when we said this, we're like, oh, we're going to kind of consider everything else as equal. Like also meaning stock price is equal. So we're going to say like, oh, time really won't affect independently like the stock price specifically. So, but it's going to be like that with all the Greeks, like the change in the interest rate, the change in the dividend rate. If, oh, sorry. Yeah, so yeah, we had that, and they're all just going to be 0. Just remember that the only Greek for the stock that's non-zero is delta, and that would actually give me a 1. So that's going to help me here because this actually is now 0 too. So that's going to help me here because anytime I have some sort of other Greek other than delta, and I wanted to have some sort of like equation with those are all going to drop out. And so it's going to be like kind of even a little nicer for those than it is for delta. Now, when we delta hedge, what we mean by that is that we really want the delta for the whole portfolio actually to be 0. So sometimes they might call it a delta neutral portfolio. Same thing. Delta hedge it. We want to try to make this portfolio where the delta is 0. So we're going to kind of add shares of stock or subtract shares of stock or like writers, buy or sell shares of stock, or maybe even some other option in order to make sure that the total delta for the whole portfolio is 0, even though the pieces won't be, but the total can be 0. And if you think about that, what does it mean for the delta for the portfolio to be 0? It means that change in portfolio compared to change in S is 0. That's delta for the portfolio. Which means, if you think about it, that if the stock price changes, so every dollar the stock price increases, what happens to the portfolio? Well, the portfolio changes by 0. That's what it's saying. In other words, it's sort of like impervious to the changes in stock price. Because stock price could really mess you up if you have this like portfolio. And if like, oh, if the stock price goes up, that could really mess you up, especially if you like write a call or something like that. And you're worried about writing a call because if the stock price goes up, oh man, you're going to have to pay more. Or if you write 100 calls or 1,000 calls. And so what you're going to do is you're going to kind of hedge it. You're going to protect yourself. That's what hedging means, but you're going to protect yourself from stock price increases by creating a portfolio where the delta is 0. So in other words, the stock price can go up or down as much as it wants. The portfolio won't change. That's what it means to be a delta for the portfolio to be 0, right? That's just what that's what delta stands for. Change in portfolio compared to change in stock. And if that's 0, that means stock can do whatever it wants and the portfolio won't change. So that's actually why a market maker would want to do this, especially if they write a bunch of options or whatever, and they're worried that the stock price change, which is the thing that changes the most, the stock price is going to change this thing, and really you're just going to be in a lot of trouble. So they hedge it, protect yourself by purchasing or writing other things in order to make a portfolio where the delta is 0. So stock price can kind of do whatever it wants and it won't really affect you, right? That's what the whole essence behind delta hedging is. Now they have a formula in there for like overnight profit. I don't really ever use that, but there is kind of like this formula, but I kind of, there's one important thing from that. It's like something with like epsilons and epsilon squareds and stuff like that. But one thing we wanted to think of, if you write a call and delta hedge it with shares of stock. So that means that you're gonna, you write a call and then you're gonna buy or sell shares of stock in order to make a delta neutral portfolio. one where the delta is 0 for the whole portfolio. And a lot of times they will also borrow money or lend money so that the initial outlay is 0. So that's fine. That just means your initial cost is 0. But then they also want to know, well, what is my overnight profit? So they'll say, what's my profit in one day if I did that? And so then they kind of give this big long formula. But the big thing that you wanted to recognize is that the profit is actually shaped like an upside down parabola. And so there's actually two places where the profit is 0. And it turns out that it's nice, there's actually kind of a nice formula for it. It's actually one standard deviation above and below the current stock price. So that means that this distance here would be kind of like one standard deviation. What they mean by that is it's like current price, sigma, square roots of, I'll just put square roots of h, but it's really 1 over 365 for a day. And for overnight, that's what they mean, but they could kind of give you the same thing for like a week's profit. But again, with all these things, like as time goes on, all these things are shifting around. It's like in a week, they're going to be nothing like what they are now. So it's kind of the problem. But I can go above and below one standard deviation to get the prices where the profit, overnight profit, is 0. And if you write a call, kind of like if the stock doesn't move by very much, actually that's when your profit is the highest. Your overnight profit, if you're a market maker that wrote a call. And if the stock price moves a lot, well, okay, now you're going to be kind of losing some more money, probably less money than if you didn't delta hedge, but as long as the price doesn't move by very much, you're still going to be okay. Okay. So this price here, just to give you, so it's current stock price plus current stock price sigma square roots of 1 over 365. And this price here would be S0 minus S sigma square roots of 1 over 365. So if they say like, oh, what prices will, where will the overnight profit break even? You can say these prices right here. They might even say, oh, for what interval of prices of like stock prices in one day will result in a negative profit. And so, it's kind of everything outside of those. Or if they say, oh, where will the profit be positive? Well, it's between those two values. Okay, so it's just kind of good. If you kind of remember this shape, it makes it pretty easy. Okay, but let's do those couple of questions here about delta hedging. And you'll see that actually it's actually very, very easy if we do it with the portfolio method. So, all right, let's see what we could do. And I kind of threw some sort of hard ones at you here, but we'll see it's actually very logical and easy to do. Okay, so stock is a price of 40. The market maker writes 100 calls and wants to delta and row hedge the position using a put of the stock and a put with a different price. So first of all, if you're going to hedge with two things, or hedge two things there, you're going to need two other things to do it with. So that's why, they're going to do stock and another put with some other strike, but it's basically still on the same stock, so that's fine. The cost, delta, and row values for the calls and the puts are here. Okay, sounds good. Then it says how much money must be borrowed or lent in order to accomplish the hedger's no cost. Okay, so let's see what we can say here. So first of all, the portfolio is, okay, I wrote 100 calls, okay, but now they want to delta hedge with a stock and puts. So I'm going to put here plus some unknown number of stocks, so N shares of S, plus some unknown number of puts. And later, I'm going to add to this, I'm going to say plus some sort of bond, because a lot of times they're going to want to do that. They're going to also borrow or lend money so that the initial cost is 0. But for now, we'll just kind of keep the bond out because that won't really matter when it comes to like the Greeks, because all the Greeks for a bond would just be 0 anyway. So, okay, but the thing is we want to delta and row hedge. So that means that I want to know delta for the portfolio, and I want that to be equal to 0. So that's cool. It's going to be negative 100 deltas for the call, plus N times delta for the stock, but that's just a 1, plus M times delta for the puts. And if I want it to be delta neutral, I guess that's going to have to be 0. But then I also want a row hedge. So I'm just going to write that right away. I'm going to row for the portfolio, but it's going to kind of be the same basic setup. Minus 100 rows for the call plus N times, well, the row for a stock is 0. Because remember, all the Greeks for a stock are 0 except for delta where it's a 1. And then plus some number of rows for the put equals 0. Because I want both of those to be hedged. So I want them to both be neutral. Or the portfolio to be neutral with respect to both. All right, now, which of these two equations do you think is going to be easier to solve? And well, I guess because the red one here has N times 0, I guess that one's going to be easier to solve. I guess I could solve that one for M. Now, they kind of make that some sort of rule that like, oh, if you ever have a delta and some other ones, solve for the other ones first and then go to delta. But we don't have to have that as a rule because we're just kind of solving this equation. And we're just like, oh, yeah, that's got N times 0. So I just want to solve for the red one first. So let me put those in. Negative 100 row for the call, 0.15, plus M row for the put, negative 0.2 equals 0. So yeah, let me solve for M. Super easy. So for M, I'm going to add the 100 times 0.15 to the other side, and then divide by negative 0.2. So just keep the signs straight. That's like your one job here is to like make sure the signs are correct. And it's harder than you think, but I got negative 75. Okay, now just check me because I could be wrong too. So, but I got M to be negative 75, but it's critical, right? The sign is the important part. So, but what does that mean? Well, that means I'm actually going to need negative 75 puts. I'm going to have to write 75 puts, and I already know that, which is great. But now I'll kind of put that into the green equation. So let me kind of do that one here. Negative 100 deltas for the call. Oops. So deltas for the call is the 0.6. Plus N times 1 plus M, negative 75. Deltas for the put, negative 0.3, equals 0 also. So easy. Okay, solve for N. So I'm going to have positive 100 times 0.6. And then maybe I'll go plus 75 times negative 0.3. So I'm going to move both those to the other side. And I got here that N was equal to 37.5. So I guess I'm going to have to buy 37.5 shares of stock. So plus 37.5 shares of stock. Okay, so actually I know the important part about my portfolio. It's going to be write 100 calls, buy 37.5 shares of stock, and write 75 puts. And we had a question is like, oh, does the detail about the strike being a different, or the strike for the put being different from the call, does that matter? And no, I think I just put that on there because if they had the same strike, then there would be a connection between these two and a connection between those two. But I just wanted to like not like have some inconsistencies. Like you should know that the delta for the call minus delta for the put equals e to the negative whatever, as long as the strike is the same, because it comes from put call parity. No, so but no, it's just kind of a detail. Like don't even worry about that here. Just it's just to kind of avoid inconsistencies. So, but yeah, great question. So here's what our portfolio is now. I'm just going to kind of give an updated portfolio now. So portfolio is negative 100 calls plus 37.5 shares of stock minus 75 puts. All right, now, so this is actually the most important part here. This is the recipe that I need to be able to delta hedge. Now, they often have this other detail about you're going to also borrow money or lend money so that you have a 0 initial outlay. So that's the part I'm going to kind of deal with here. They said how much must be borrowed or lent in order to make sure that the the cost is 0. So here's what I'm going to say. I'm going to say, okay, plus some sort of bond here. The bond didn't really play a role with all the Greek stuff, so I just kind of kept it out of there. But now I'll put it in because I know that I'm going to have to borrow or lend somehow in order to make the cost equal 0. But I know that cost follows the same sign pattern. Cost is -100 costs of a call, 382, plus 37.5 costs of a share of stock, and stocks are priced 40, have a current price of 40, minus 75 times the price of a put. Oh, that's in the table too, 219, plus some unknown bond equals 0. Awesome. Okay, well, actually, so I could solve for B. B equals, and I'm just gonna move everything over to the other side. And again, just be careful about the signs. That's all. So I've got positive 100 times 3.82 minus 37.5 times 40 plus 75 times 219. And I get that B is -953.75. So what does that mean? Okay, well, B is -953. So that means that if I kind of added that to my portfolio, I would go -953.75. So what do I know? Well, long is lend, minus is borrow. I guess I'm going to have to borrow $953 to do it. If you wanted, you could actually have just done cost without the bond, and it would have turned out to be cost positive $953. So you're like, oh, if it costs $953, I'm going to have to borrow that to pay for it. But this is actually kind of more consistent, less to think about. Long is lend, minus is borrow, we're good to go. Okay, but we put these in as unknowns, and then we let the math solve for it so that we can just kind of do what we got to do. We can just kind of put in, let the signs speak for themselves. Okay. All right, let's do another example. So the market maker writes 50 puts on a stock and wishes to delta hedge her position with shares of stock. Okay, so I'm just going to write that down here. Portfolio is -50 P's plus some unknown number of shares of stock. Okay, no problem. All right, just put it down there. And then probably they're going to do something with a bond, you know, like to make sure that there's, you know, so that it has a 0 cost. That's pretty much always the case with delta hedging, but maybe it's not so important sometimes. But all right, so then here, the stock has a current price of 50 and the put has a price of 312. The delta is 0.3. Continuous rate of interest is 4%. A day later, the stock price is 82, cost is 280. Determine the overnight profit for the market maker. All right, overnight profit. All right. So here's where you could kind of memorize a formula maybe, but then sometimes it has like the deltas and the gammas and all that, and then maybe they don't give you all that information. But actually, we're going to do it like we did before. Oh, profit is payoff minus future value of the cost. So we're going to kind of assume that it has a 0 cost, right? Because we're going to borrow or lend to be able to have a 0 cost. You don't have to do that, but we'll do that. But yeah, we're just going to do that. And then that's how we're going to do our profit. So just kind of like the same way we did back on day 1. So let me first find the number of shares of stock I need. So delta portfolio is -50 deltas for the put. So I'll put as a delta of -0.3 plus n times the delta for a stock, which is 1. And I want that to be 0 because I want to delta hedge it. So the delta portfolio should be 0. And that gives me n equals, so I guess 50 times -0.3, which is what, -15. And again, I would use the calculator totally for it, but that one's kind of easy. So great. That means my portfolio is going to be -50 puts minus 15 shares of stock. So it feels a little weird because I'm like, oh, I'm shorting puts and shorting stocks, but actually that is the right thing to do. And I think for here now, I think I will do the thing where I'm gonna find out how much I need to borrow or lend so that my initial cost is 0. So that way I'll have my future value of my cost will be 0, and I'll be able to just kind of do it from there. So I'm gonna have here that this is plus bond. And so my cost is now gonna be minus 50 times the cost of a put, 312. Minus 15 times the cost of a stock. And I'm looking back up here for this. So minus 15 for a cost of a stock, and the cost of the stock is currently 80. And then plus a certain bond, and I want the cost also to be 0. Okay, so let's find out what B is. So B, I guess, is going to be a positive 50 times 312, and then plus 15 times 80. 1356. So I'll just write that one more time up here. My portfolio now is negative 50 Ps minus 15 shares of stock plus 1356. So long is lend. So I'm actually lending out 1356. But actually I don't need to know that in this problem. No problem. So but this is my portfolio now, and this portfolio has 0 cost. If I did it before without the B, the portfolio doesn't have a 0 cost. So when I did profit, I'd have to find out the cost and then accumulate it with interest. But we're going to see that actually, we're going to do all that, but it's just going to feel a little bit easier here. Okay, but this is a portfolio with 0 cost portfolio. All right, now let's go 1 day later. 1 day later. All right. So I want the profit in the next day, but because the cost is 0, profit equals payoff. So profit equals payoff minus future value of 0, right? Because it has 0 cost, so future value of the cost. So basically it's just the payoff. Now, what is the payoff of this thing? Oh, well, beautiful. Since I have the portfolio, the payoff is, I'm just going to keep the same sign pattern stuff. Minus 50 times the put, minus 15 times the stock, and then plus 1356. But remember, with stocks and with bonds, I just have to accumulate it with interest. So I'm just going to have this times e to the 0.04 over 365, because it's just a day's worth of interest, which is fine. It's no problem. It's just a bond and move it forward. Now, this is the thing that might be a little bit surprising in a way. And different books handle this different ways, and I kind of don't really like the way they do it. For us, we're just going to keep it simple. Just I hope you do too. But so basically, it's the payoff, and I had 15 puts. So the put here, for me, it's just going to be the value of the put. Before, when we did these, we kind of thought like, oh, what's the stock price? Is it above or below the strike? And does it pay or not? But that was because it was at expiration. Right here, we're not at expiration, we're like a day later, right? So the best we can do is just, our payoff would be if we just sold the put and cashed in on it and just found like sold it to somebody else or something like that. So we just kind of put the current price there because that's how much it's worth to us. So the current price is, okay, the puts cost 280, and simply that's it. And the stocks are now worth 82. So I'm just gonna just that, and that's it. This is my profit. This is my overnight profit. Let's see what we get. Negative 50 times 2.8 minus 15 times 82 plus 1356 times e to the 0.04 over 365. Negative 13.85. And that's my overnight profit. Now, if you've done these before, you might have seen them do something like this, where they're like, oh, okay, instead of 280, I'm actually going to do like 280 minus 312. And then for the 82, I'm actually going to do 82 minus 80. And then for this one, I'm actually going to do e to the 0.04 over 365 and then minus a 1 or something like that. You might have seen that. And we're doing the same basic thing, only this always kind of didn't feel right to me. And it's actually like mathematically okay, but sort of in a way like not really right. So because the thing that didn't sit with me right on this was, this is something that we paid a day before. Shouldn't we accumulate that with interest? Why are we just comparing these the same now? And it turns out it's okay, but it's kind of like sort of for a shady reason that they don't really tell you. So I actually don't like that at all. So I'm never going to do that. And you don't need to. It's just like, it's mathematically it equals what we did. But I think some people like that a little bit better. But just keep in mind, like, not to do some sort of hybrid between that and this. Either do one or do the other. And if you're cool with that way, just do it. And if you're fine with it, I'm totally glad with that too. But if you kind of put it in terms of what we've done, it fits with that as well. So if you like this better, it's real simple. Okay, but just keep in mind, sort of like with the arbitrage stuff, that there are these two different ways, and like, pick one to be consistent, actually see the two and see the power of knowing both, and then picking the one that like works best for you. And sometimes knowing that the two of them are out there is valuable. So, all right, last delta hedging one, see kind of what else that we could do with this method with the portfolios. Okay, a stock has a price that's log normally distributed. Okay, that's nice. Or they could say Black-Scholes framework, same thing. Okay, a market maker writes 1,000 European puts, and Delta hedges her position with calls on the same stock. Okay, so I guess we're going to do my portfolio now, minus 1,000 puts, and then plus a certain number of calls. So notice how we're not delta hedging with stock now, but we're delta hedging it with calls. And maybe they have the same strike, maybe they don't, not really sure. I guess they didn't really say anything about that, so maybe it doesn't matter. All right, and then after 5 days, the stock price changes, so the deltas change. So determine the amount of calls needed to be bought or sold in order to maintain a delta neutral portfolio using the values from the table. All right. So first things first, I guess I need to know N. I need to know the number of calls that I'm dealing with. So that's okay, that's pretty routine. Delta portfolio is negative 1,000 deltas for the put plus N deltas for the call. And I want that to be equal to 0. No problem. Negative 1,000 delta for the put. Okay, that's right over here, negative 0.5. Plus N deltas for the call, 0.28 equals 0. And let me find out what N is then. That should be easy enough here. So I'm going to go positive 1,000 times negative 0.5, and then divided by 0.28. Ooh, I got kind of a nasty number. Negatives, negative 1785.7, whatever. So I think what I'm going to do is, again, because I care about long and short, I think what I'll do is I'll make this I'll keep the negative separate, and I'll handle the negative myself. So I'm gonna kind of multiply this by -1 and store that in for X. So I'm going to store just the positive 1785 for X. Okay, so maybe I'll kind of put that on here. Positive 1785 stored in for X. So then my portfolio really is minus 1,000 P's minus X calls. Right, and if you want, you can keep X as negative 1785, or even just write it in there, negative 1785. But sign is probably going to be important here. So I just want to make sure that I don't kind of like trip up over the sign myself. So I'm going to handle the sign manually because I don't want the calculator to mess up on me. Okay. So, but I definitely know I need to be short 1,785 of these calls. So however you handle that, that's fine. You can do plus X if X is negative, or you can make X positive and just write minus X shares, X calls here. Now, normally I'd have to do plus a bond, but they don't really ask me anything about profit or anything like that. And the bond's not going to really make a difference. So I'm going to just forego the whole bond thing because it's not really necessary here. Because they just want to know I'm going to like, well, I'm going to need to buy or sell more shares, more calls in a few days. But I don't care about how much money I have to spend on all that. It won't really be affected by the bond. So I'm just going to leave that off, and I'm going to say now in 5 days. So the thing is, yeah, like these things are constantly getting out of like unbalanced. Like a few days later, if the delta for the call like changed, now this thing won't equal 0, right? Or if the delta for the put changes, they're not going to change and keep it all 0. I have to like constantly rebalance these things, these portfolios, to make sure that they remain delta neutral. So that's what they're doing here on this one. Now the deltas kind of went out of whack a little bit. So it's not going to have a delta 0. So I just need to know how many shares or how many calls do I need to purchase or sell to make it back into delta being 0. So here's what I'm going to do. I'm going to think of my portfolio now is, okay, well, minus 1,000 puts, minus X calls. But I know that I'm going to need to rebalance, and I'm going to want to use more. They said how many amount of calls need to be bought or sold. So I know I'm going to have to like kind of purchase or sell more shares, more calls. So I'm going to put here plus M kind of calls again, because I really want the delta for this portfolio again to be 0. So I'm going to have negative 1,000 deltas for the put. And now I kind of come over here to the new delta for the put. So negative 0.57 minus X deltas for the call, 0.22, plus M deltas for the call, 0.22. So again, 0.22, and it makes sense because it's more calls of the same delta. So that's good. But I want it to be delta neutral, so I want that delta to be 0. But great, I'll solve for M and see what I get here. So positive 1,000 times negative 0.57 plus X times 0.22, and then all that divided by a 0.22. And I got that M was negative 805.194 whatever. So I guess I'm going to have to, since it's negative, I know I'm going to have to go negative 800 more calls. So I guess I'm going to have to write 805 calls to make sure that later it's also delta neutral. So that's kind of like 805 more calls, because I've already written 1,700 calls. So I need to write 800 more. So maybe I'll put that even in here, 800 more calls to be able to do that. Okay, so any questions about that? So it can actually be pretty easy, these delta hedging questions. They're actually like kind of pretty routine if you're comfortable with the portfolio notation. Actually, it's like really nice, and just kind of understanding what you're doing makes a big difference. Okay. All right, so let's move on to our last segment for today, which is, okay, now we're gonna just kind of pick those, the forward start, the chooser, and I put one more kind of option that or one more sort of derivative that they love to ask about, dealing with maxes and mins. But we're gonna notice that the process for us solving these is gonna be the same for all three. And so we're just gonna see like kind of 3 different ways to apply the same technique. Okay, and so what we're going to do is we're really doing risk neutral pricing again, where we're finding the expected value and bringing it back. But prepaid forwards, that's exactly what a prepaid forward is that it says that it's the time value now in order to receive that particular thing later. But now we want to talk about a couple of like prepaid forwards that are maybe not very non-traditional. here. Like, what's the prepaid forward of a max or something, right? It's not like a share of stock. Before we did, okay, prepaid forward of a K, awesome. So if I'm here at little t and I wanted to get K here, oh, K, easy. It's just discount it with interest. So K e to the negative R times T minus T. No problem. Prepaid forward of a stock, same place. But if I had a share of stock here and I wanted to get exactly one share, well, there's where we had the three cases. Either it was the current price at time t, if there was no dividends, then it doesn't really matter if I buy it now or buy it later, doesn't matter. So this is for no divs. Or it could be current price minus the dividends, whether that's discrete or continuous. So I'll have current price minus present value of divs if I've got discrete dividends. And then current price minus, so e to the negative delta times t minus t for continuous dividends. So that's all just review. We kind of knew that already before anyway. So, but yeah, just, so that's how we did that. That's how we would find the current price here. It's basically risk neutral pricing, whether we realize it or not. It is actually risk neutral pricing. We're doing the risk neutral expected value there, bringing it back. Okay. Now, what if the thing I'm trying to do, the prepaid forward, isn't a stock or a strike or a currency or something like that? So the cool part is that, well, it's actually okay. So here I'm standing at time 0, it looks like on this particular one. So the prepaid forward, if I'm standing at time 0, and I want to receive exactly one of these, a max of ST minus K and 0 at time capital T. How much should I pay at time 0 in order to receive exactly this payout in the future? And you might recognize, like, hey, that kind of looks like a call. And that's exactly, so this is actually what Black-Scholes did. They said, okay, I'm going to find the risk neutral expected value of this, bring it back. Great. For us, that's the same as the prepaid forward. But this is actually the prepaid forward to bring this back. I'm not going to discount with interest here or something like that. It's actually the Black-Scholes call price. That would be the prepaid forward of this thing. Super weird, but it's, again, I'm just trying to think of like discounting. Notice how it's not max of whatever times e to the negative delta t, or sorry, e to the negative RT. That's not what it is. It's not that minus interest. It's much more intricate and complicated, but it's okay. I can do it. I know to bring that particular thing back, it's the Black-Scholes price of a call. If I'm here at time little t, so let's say I'm at time little t, so I'm going to move the guy forward. And I wanted to receive max of K minus ST and 0 here. Well, I guess that would be now a put price. So the put on the stock with that strike, but now with, I guess, T minus T to go. Right? That's how much time is left in that option. But I could ask for the prepaid forward of this max, either a max of S minus K or K minus S and 0. No problem. Bringing those back is just the Black-Scholes price. Easy. Now, what if it's a little bit weirder? And okay, let's say I'm back at 0 again. And I want to know if I'm right here. So, or sorry, so it expires at time little t, but I want to receive a call on a stock with a different stock as the strike, and that call has T minus T to go. How do I do the prepaid forward of a call? What is that going to be? Well, I can kind of think of it in terms of like, well, this thing here, well, it'll expire as the max of ST minus QT and 0. So I'd ultimately want to receive something equivalent to that. But that I could actually think about as moving backwards. I mean, I could kind of go a roundabout way of bringing this thing back. I can actually move it forward first and then bring it back. But this is actually a call, at time 0 now on the stock with the strike of Q, but now over the whole period of time capital T. So what did we learn from this? What does this mean? Well, okay, in short, the prepaid forward of a call is a longer call. And the prepaid forward of a put would be a longer put. I'm basically trying to move this call backwards, and it's okay, I can do it, especially if it's going to expire out here anyway. It would just be kind of a call priced at time 0 that would still expire at the same spot. So it's just a longer call. That's all I would do. And a put works the same way. So I think on, I don't know, on the 3rd seminar or whatever, we had this sort of compound options, a call on put and a put on put. And for us, if we did put call parity, it would be prepaid forward. So this option actually is from 0 to little t. So it's the prepaid forward of the first thing, put S, K, T minus T to go, minus the prepaid forward of X, and X is just a dollar amount. So it's just like X e to the negative R little t. Because this option here, the outer call, is over this period of time. So 0 to little t, it's got to expire there. But then at time little t, the thing that it's gonna give me is this put that has T minus T to go. So that's cool. But at any rate, I can say the prepaid forward of that put now, okay, prepaid forward of a put will be a longer put. That put was originally going to expire at time capital T, but now the prepaid forward would be a put now at time 0, SK, over the whole length of time T, and then minus that XE to the negative R little t. So the prepaid forward is the way that we're going to kind of think about moving things back in time. I'm going to try to get things that look like this or this, max of S minus K and 0 or K minus S and 0, because this is now one new thing that the prepaid forward of that is just a call or a put. And I also have this added benefit that if I do the prepaid forward of a call or put, it becomes a longer call or put. So it's like really nice. I just need to know when the original thing was going to expire, and it's going to have to still expire at the same time, but for like, it'll just have a little longer duration because I'll be pricing it earlier. Okay, but that's it. These are going to make you unstoppable. It's going to be great. Okay, especially for these couple of options that we're going to talk about here. Okay, so let's see how this applies. So the technique that we're going to do for all three of these is going to be the same. We're going to first write an expression for the value of something later. And then, so usually it'll be kind of like the forward start, the choosers, this kind of like this sort of like thing that happens in the middle. So we're going to write the expression as if we were standing at that time and we knew everything at that time. And then I'm going to kind of do the prepaid forward of all that to move it backwards, right? That's all we're going to do. So with a forward start, remember with a forward start, the things that we knew were, well, we knew it was a call or a put. We would pick which one we were going to do. We'd know the times, and we'd know that we'd have some sort of like fractional amount here that we want to set our K to be equal to. So we know it's going to be K times K is equal to some fractional amount of the stock price at time little t, but we won't lock in K until we get to time little t. But we will be able to choose what fractional amount we want. We have to know that at time 0. And then at time 1, we're going to lock in K to be equal to FST. But then once it's here, okay, then that won't change anymore. But over this period of time, the K is kind of, dependent on the stock price. Okay, but only here, once it gets to here, then it's locked in. So I know that the K over this period of time is going to be solid. It's concrete, it's known. But the stock price is still going to be able to kind of like go up or down or whatever, we'll see. Okay, so here's what I'm going to do. What if I was right here at time t, time little t, what is the value of this thing now? So let's just illustrate it with a call. It could be for a put too, but we'll just do a call because it's a little simpler. So if I'm at time t, then this is going to be a call at time t on the stock. The strike now is going to be, now I'm going to know the strike. It's going to be FST. So, and then this is just some number. It's a concrete number, even though it looks like a stock, it's not changing anymore. So that's good. And I know I'm going to have t minus t to go. So if I'm at time t, I'll know everything here. I can do Black-Scholes, and Black-Scholes will say that this is going to be, okay, prepaid forward. So now I'm over the red interval here. So I'm going to do a prepaid forward from little t to capital T of the stock, N of D1, minus K. So that's actually, now it's actually a legit K. It's a dollar amount, even though it looks like it's related to the stock, but it's FST e to the negative R times time, and then N of D2. Okay, but that amount is just a fixed dollar amount now, it's fine. That won't change over here, but the stock itself, you know, still could wiggle a little bit, but the strike is locked in. But okay, well, actually the prepaid forward here, what is that going to be? Well, that's going to be current price minus dividends. So I'm going to have S little t e to the negative delta times time, t minus t, because that's how far that one has to go, the red line. And then N of D1 minus FST e to the negative R times time, N of D2. And now here's kind of the cool part. This is what happens is that D1, and again, if I'm at time little t, D1, what is it? Well, you could either do log of, you know, this over this, like we did, like we had, or you could do kind of the one that we're more used to, log of S over K. So it's ST over K, and what was my K? FST plus R minus delta plus 1/2 sigma squared times time over sigma square roots of time. But the neat part is that the STs now cancel. And if you think about it, that's the only thing that I wouldn't have known if I was at time 0 instead of time little t. Everything else I'll know at time 0. But the thing that I'm uncertain about canceled out, washed out. That's great. That's great for me. So now I can actually find the D1. I can actually even find this D1 if I was at time 0 instead. It has nothing to do with t. I'll know all that stuff before I get there. So the cool part is that, to make a long story short here, I'll know this, I'll know this, I'll know this, I'll know all this. The only thing is that I'm not going to know is, if I'm at time 0, is this ST. But that's the beauty of this, because now I know that this whole thing is just, I could kind of factor out the ST, and it's just going to be ST times some sort of constant. So now if I go find the value at time 0, I know that the call price is just going to be ST times some number. So to bring it back, I'm just going to do the prepaid forward of ST times some constant. So I'm going to say the prepaid forward now 0 to t of ST times whatever that constant is. And okay, well, whenever I do a constant times, you know, something prepaid for, I'm just going to do the prepaid forward of this times that constant. And what's the prepaid forward of ST? Well, it would be now current price S0 e to the negative delta times, well, the prepaid forward over that interval 0 to little t. So e to the negative delta times little t. And then all of that times this whole constant here. And I'll be able to get the price. I'll be able to get the price now. So it's pretty interesting, but I have to do it in these like 2 steps here. So let's do an example, and we'll see it in real life here. Okay, so but we're going to do that process, and I'll do the exact same process again so that you could see it. Okay, stock is log normally distributed. You have a 3-year forward start put that'll allow you to lock in the strike in 2 years at 90% of the stock price at that point. So let me draw a little timeline here. So here I'm going to lock in K at 0.9 S2. And it's a put. So that's okay. But notice how I know time 2, I know time 3, I know what's going to happen at time 2. That's fine. And okay, just want to find out then the price of this option. So I'm going to do this 2-step process. I'll find out what is the value of it in 2 years. So if I'm standing at time 2, well, it's just going to be a put at that time with 0.9s2 as the strike with 1 year to go. Easy, no problem. I could do Black-Scholes for that. Negative prepaid forward over the interval 2 to 3. So I'm standing at 2, looking to 3. So I'm going to go prepaid forward over 2 to 3 of the stock and of negative D1 plus, well, this is now a K, so 0.9s2 e to the negative R for 1 year, and the R is 4%, so negative 0.04, N of negative D2. And the prepaid forward of S, what's that going to be? Negative S2 e to the negative delta for 1 year, 0.03, N of negative D1, plus 0.9 S2 e to the negative 0.04, N of negative D2, no problem. So my D2, or my D1, is just going to be log of S over K. So S was S2, K was 0.9 S2, and then R minus plus R minus delta, so 0.04 minus 0.03 plus 1/2 0.3 squared times 1 year to go over 0.3 times square root of 1. And the cool part, the S2s cancel, so I actually know what this D2 is going to be, even though, or this D1 is going to be, even though it's actually in the future, and it depends on the price at time 2, but the way that they've defined it, I'm able to find out this is 53454. So then I can get D2 and I can get everything. So I'm actually going to get D1 and D2 for sake of time. I'll show you what we all get. We're going to get, well, I'm going to be able to factor out the S2 here, and I'm going to get negative e to the negative 0.03. N of negative D1, I'm going to be able to get, because I got D1 here. So N of negative D1, I'm going to be able to get. And then here I've got 0.9. I factored out the S2. So I'm going to have 0.9 e to the negative 0.04, N of negative D2. And I'm going to be able to get D2 because I've got D1. And D2 would just be this number minus 0.3 square roots of 1, right? So I'm just going to be able to get D2 also. I'm going to get all those numbers. This is just going to be some sort of number here. Okay, and I don't have that number, sorry. Sorry. I don't know what the number is, but it's just going to be some number like, I don't know, 3 or something, who knows? It's just going to be some number. But now that I've got the value at time 2, now I can take that whole thing and now just like kind of project it back, prepaid forward back to time 0. So I'm just going to be doing prepaid forward of S2 times that number, whatever it is. Okay, what's the prepaid forward of S2? Well, over this year, well, it's going to be current price S0 minus 2 years worth of dividends, so minus 0.03 times 2. All that times that number. And the final answer here is 4.8566. Okay, but the process is the thing that's important. I'm going to bring it back. All that will just be able to be computable, all the stuff inside the parentheses here, and go ahead and write it and just find out what the number is. I should have wrote that down, sorry, and be able to take it back. Okay, that process. Now let's see that process again on a different question. Okay, so for this, here's the another kind of question that they'll ask where we're going to do the same thing, find the value in the future, and then prepaid forward it back, bring it back. For this, though, just wanted to talk a minute about sort of the algebra that you could do with maxes and mins. So if I've got the maximum of A and B, So if A is bigger, then it'll be A. If B is bigger, it'll be B, right? But the cool thing is I can add and subtract a value. I could like, here I have a plus C on the outside, so I could subtract C on the inside, and it'll be max of A minus C and B minus C. And the cool thing is it works for minimums also. If I add a C to the outside, I could subtract a C on the inside. So it'll be min of A minus C and B minus C. So that's cool. So that kind of works. Yeah, it's kind of how you'd expect it. This is where it's going to be a little bit weird, but it's going to be nice to know. So I could actually also factor a C out. So basically I'm multiplying the outside of a C, so I'm going to have to divide the inside of the C by a C. So this is going to be max of A over C and B over C, right? I'm multiplying the outside, dividing the inside. However, there's a stipulation. The stipulation is that C actually has to be positive. Because if C is negative, then this is actually going to turn into a minimum. And I'll illustrate that for you here too. So max of 2 and 4. Well, clearly that's 4, right? So if I factored out at 2, I'd have 2 times max of 1 and 2. Right? So I'd multiply the outside, divide the inside, or kind of factor 2 out if you want, that's fine. So it's going to be 2 times, oh, what's the max of 1 and 2? That's a 2. Okay, 4. Okay, that's what I should get because the max is a 4. But if I did a negative 2 max of, and now I divide the insides by a negative 2. So I'd have 2 over negative 2, 4 over negative 2. So that's minus 1 and minus 2. What's the max of minus 1 and minus 2? It's actually minus 1. So this is going to be a negative 2 times, so that negative 2 there, times the max, which is negative 1 in this case. And ooh, it's not the same as those. But if I were to change this to a minimum, that's okay. Oh, now I'm selecting the negative 2 there. And I will get negative 2 times negative 2, which is a 4, which is the answer I should have gotten anyway. Okay. Now, as you can imagine, that same thing is going to translate even to minimums. So I can pull out a positive number, no problem. But if it's negative, I just have to change it to a max. So if I factor out a C out of a minimum, great. A over C, B over C, if C is positive. But if C is negative, then it's going to change over to a max. So just be aware of that it's kind of okay to do, but with negatives, it just acts a little weird. But actually, that's going to be good for us because it's going to allow us a way to change a minimum to a maximum. And the easiest way would be if I multiplied and divided by a minus 1. So I could actually have a negative max equals of negative A and negative B. So a minimum I could turn into a maximum, and a maximum I could turn into a minimum. Now for us, maximums are going to be better for us because we're really trying to seek out and try to find max of S minus K and K minus S and 0, right? I'm really looking for maxes. Maxes are my preference. But if they give me some problem that's with a minimum, that's okay. We can change it into a maximum easily by negating the outside and inside. It just changes it over. Okay, and we're really using, I guess, this property here with C equals negative 1. That's really what we're doing. Okay, now let's see that here because they will give you questions like this. So here's one of the questions. It says, the CEO of a company would like to give a bonus to the CFO for all her hard work. The CEO offers to give her in 1 year 100 shares of the company or 40,000, whichever is less. So that's in 1 year. So notice here, the value in 1 year is the minimum of 40,000 or 100 shares of stock. So 100 S1s specifically, because whatever the price is at time 1, that's what the share will be. So As I hear, shares of the company currently sell for $3.50, and they have a continuous dividend rate of 2%, a 1-year 400 strike European call on the stock currently costs 40 or 21.44. All right, what is that? A call on the stock with strike 400 with a year to go. So that's a currently one. So that's a time zero call, a 1-year 400 strike European call currently costs 21.44. So find the value of the bonus today. Okay, so we're going to be able to use this somehow. We're just going to have to see how. Okay, so here's the process. Our goal, if we're going to be able to move this thing back, we're going to want to somehow end up with, oops, not min, max of S minus 400 and 0. Because if I had this at time 1, if I have this at time 1, S minus K and 0, the max, the prepaid forward of that is exactly this call. So when I bring it back to time 0, I'm going to get this call so I can use its price to kind of help me out, right? So that's going to be, this is sort of my goal. I'm going to want to see things that I want to try to get this in there somehow. Okay, but the thing is I've got a minimum. So I know I'm going to have to like negate, and you can do this in a bunch of different orders. I'm going to do it kind of in the nicest one, but I want you to try doing it in different orders later to see if you can get the same answer. So I know that to change the min to a max, I'm going to have to negate some stuff. So that helps me because I probably am going to want, first of all, a 400 minus S inside the minimum. Because if I have 400 minus S inside the minimum, then when I change it to a max, I'll negate it, which will flip it, which will give me the S minus 400. So, okay, so we can kind of think about that. So if I'm working with the minimum, I'm going to want these reversed. So I'm going to subtract out, well, add on the outside, subtract on the inside 100 S1s. I'm going to do that first. So 100 S1 plus min of 400,000 or 40,000 minus 100 S1s and 0. So all I did was subtract 100 S1s inside and added 100 S1 outside. Okay, so that's all I did there. And then the other one is, I think I'm going to factor out 100, so then it can just be out of per S1s instead of 100 S1s. So this is going to be 100 S1 plus 100 min 400 minus S1 comma 0. And now I'm going to change it to a max. I'm going to negate the outside, negate the inside of the min. 100 S1 minus 100 max of minus this and minus 0. So S1 minus 400 and 0. But beautiful, that's what I wanted. So now I can actually find the time 0 price by just taking the prepaid forward of all this. So V0 is prepaid forward of 100 S1 minus 100 prepaid forward, or minus prepaid forward of this too. So prepaid forward of this max thing. And I could have written this as 100 prepaid forwards of S1. So I don't know why I didn't, but that's okay. But actually prepaid forward of a stock. Oh, okay, great. I could do that. Prepaid forward of a stock is just current stock price, which is what they say, 350 e to the negative 1 year's worth of dividends, right? Current stock price minus dividends. And dividends, they said, were 2%. So I'm just going to go minus 0.02. And then minus 100. And then the prepaid forward of this is actually that call, because this is the payoff of the call. So to bring it back to time 0, that would be the price of the call, S401. And these are the ones that were 21.44. So now I can compute all this out. Great. And I can get my answer this way. And long story short, 32,162. should be our answer there. Okay, but again, the process was the important part. Just wanted to show you one that actually was a min. If it starts as a max, it's a little bit easier. And a lot of times that's the question they give you. I just wanted to give you a little bit of a harder one. So if they asked about the minimum. So the minimum has an extra layer of, you have to change it to a max by negating. Now, one thing I just wanted to mention was, if you change the min to a max too early, it almost gets more confusing. Even though you kind of have that itch to do that, I would do it as late as possible. So try it though. Try changing it early, or try, whoa, what would happen if I factored out the 400 instead? And in that case, it would have just ended up the opposite. You would have gotten a put. But if you know the call, you wanted the put, you could do put call parity. And then you do prepaid forward of S minus prepaid forward of 400. And yeah, you could kind of get things that way too. Okay. All right, one last example then was the chooser options. So with a chooser option, remember what we did? Well, at time 0, we knew K, little t, and capital T. And then at time little t, we picked call or put, whichever was better at that time. So here's what we're going to do. Same sort of thing. VT. What is VT? Well, VT is, the value here is going to be, well, how do you think I'm going to pick the call or the put? Well, I'm going to pick the one that's more valuable. So I'm going to pick the max of a call at time t on the stock with a strike and t minus t to go, or a put at time t on the stock with the strike with t minus t to go there too. Whichever one is higher in price, that's the one I want to pick. So it actually has a max, that's great, but I need a max of S minus K and 0. But this is a call and a put. But I think back to put call parity. Call minus put is like prepaid stock minus prepaid strike, like stock minus strike. Oh, maybe that's what I want to do. So what will kind of probably usually work out the best is if I subtract the put from the inside, so I'd have to add it to the outside. So this is going to be a put S K T minus T to go plus the max of call minus put and put minus put, so 0. But then I'm going to do, then I'm going to work the put call parity here to have like prepaid forward stock minus prepaid forward strike. And then I'm going to kind of work that down. And then I'm going to do the prepaid forward of this minus the prepaid forward of what I get there. And I'm going to be able to get that. Okay, so let's see that one in action too. It's too, I don't think it's very helpful with all the details being so general here. So let's look at an example where it's probably harder than the ones that you've maybe encountered, but I just wanted to, again, give you something a little bit different. Okay, so here we are. We've got purchase an option that allows you to choose in 3 years whether to receive a 2-year 100 strike call or put on a stock. Draw it out. So basically look at 0, 3, and 5, right? And here I'm going to get a call with strike 100 with 2 years to go. Maybe I'll say call or put here. I'm going to be able to choose that at that time. Okay, and I know that the strikes are 100, so that's good. And okay, so the stock has a current price of 95, so S0 is 95. Dividends is 2%, and they have here the premiums or the cost of all these different puts. So these are all for puts with different strikes, different durations are in this table. And okay, the risk-free rate is 5%, so R is 0.05. So determine the price of the option. Okay, well, let's do it. Let's go through the details now. So I first want to find the value at time 3. So what's the value at time 3? Well, it's the max of a call at time 3 on the stock with a strike of 100 and 2 years to go, or a put at time 3 on the stock with a strike of 100 with 2 years to go. One of the two. Whichever one's more valuable, that's the one I want. So I'm going to want, I know I'm going to want put call parity. That's kind of the gimmick here, the trick to make it work. So I'm going to take the put out. So I'm going to add the put on the outside, subtract the put on the inside. So this is going to be a put at time 3, stock, strike, 2 years to go, plus max of call minus put and 0. And that's the call at 3 minus the put at 3. So, maybe I'll actually make that a little bit more verbose so we could see it here. Call at 3, S100 with 2 years to go, minus put at time 3, S100, 2 years to go, time 2. So now I'm looking over this sort of like green section of the timeline here. I'm at time 3, looking to time 5, and I'm trying to do that. So, okay, great. But we want to see that first component of the max as call minus put. Well, I'm going to think of prepaid forward of stock minus prepaid forward of the strike. So the put, I'm just going to, unfortunately, there's nothing I can really do with this one. So I'm just going to kind of just sort of write that. I'm just going to keep writing that one down. I don't want to have to rewrite it all the time. But so this is the max of, okay, well, prepaid forward of the stock, and prepaid forward over what interval? Well, I guess prepaid forward over 3 to 5, because that's the one we're looking at. 3 to 5, prepaid forward of the stock minus prepaid forward, also over 3 to 5, of this strike of 100. Just did put call parity on call minus put. Okay, so what is that going to be? Well, the put again plus the max of, okay, prepaid forward of the stock. So if I'm at time 3, what's the prepaid forward of the stock now? Well, current stock price, which is S3 minus dividends. E to the, well, I guess there I've got 2 years worth of dividends that I have to kind of take out. E to the negative 0.02 times 2. Minus the strike, E to the negative, well, 2 years worth of interest. So E to the negative 0.05 times 2. Okay, now it's a little bit pesky here because it's not stock minus strike here right away, right? It's like some extra shares of stock and some weird strike thing, but the strike is flexible, but I do need it to be over exactly 1 share of stock. So I'm going to do one more thing. I'm going to kind of pull this out. So I'm going to multiply the outside by E to the negative 0.02, multiply the inside by E to the negative 0.02 times 2. So I'm going to have here again, puts still there, plus E to the negative 0.04 max of, and now I guess I'm dividing by E to the negative 0.04 or multiplying by E to the positive 0.04, however you want to see it, but I've got S3 minus 100. So that's E to the negative 0.1, but then plus 0.04 is, I guess, negative E to the negative 0.06 now. And let me just compute that out. What is E to the negative 0.06? 100 E negative 0.06, 94.18. Okay, that's kind of cool, actually. Because now I can do the value at time 0 is now, okay, now I can do the prepaid forward. So it's going to be the prepaid forward now over 0 to 3. Now I'm trying to take everything back here. So if I'm at time 0, I want to do the prepaid forward of this expression at time 3 back to there. So I'm going to do prepaid forward 0 to 3 of this put at time 3 on the stock, strike of 100, 2 years to go, plus E to the negative 0.04 times, well, prepaid forward of this, but actually I know what the prepaid forward of that's going to be, so I'm not going to write it. I'm prepaid forward of S minus K, that's what, a call or a put? It's a call. So this is going to be a call on the stock with strike 94.18 now, with 3 years to go, because it's going to pay the max at time 3. So it becomes like a 3-year call. Okay, now that's going to be pretty nice because prepaid forward of a put is just a longer put, but the prepaid forward of this max became a call. Okay, so it's like, yeah, it's kind of neat. It kind of works all together. So this prepaid forward of a put, it was a 2-year put, but I'm bringing it back 3 more years. So now it's going to be a put at time 0 on the stock, strike 100 with 5 years to go, plus e to the negative 0.04. Well, a call on the stock would strike 94.18 now with 3 years to go. So, but in the table, I just have puts. So I guess I'm gonna have to do put call parity. But the one that I'm looking for is a 3-year with strike 94.18. So I know, just to kind of draw it up here, that call minus the put price is going to be now the prepaid forward of the stock over 0 to 3 now over this red interval up here. So that'll be current price minus dividends. Current price now is actually current price at 0, because I do want the prepaid forward over 0 to 3. So current price is, what they say, 95 e to the negative 3 years worth of dividends, 0.02 times 3, minus the prepaid forward on the strike. Well, strike is 94.18 e to the negative point. Well, now I've got 3 years worth of interest here. So e to the negative 0.05 times 3. And okay, maybe I'll just kind of calculate that call out real quick. Oh, well, I did it already, just for time, 22,456. Store that into X. But yeah, I'll just kind of throw that in here. That is actually this price for the call. Okay, one last thing to do, and we're done here, because now I just need to know, well, what was the price of this put? So this put became, well, now it's a 5-year put with a strike 100. And that one, oh, sweet. I already have the premium. I don't have to do put call parity. Thank goodness, because that's kind of annoying, right? So 1815 plus e to the negative 0.04 times that X number, which ultimately gives us 3973. Okay, and when you do this with the chooser option, you should always expect a put and a call. A put from the one that you pull out here, but then this thing will turn into like a call. So you'll always have like one and the other. They won't have the same strike and time, but you'll kind of have one and the other. So see that. But at any rate, I hope these examples were good. I hope, actually, I hope you benefited from the seminar. Thank you guys so much for coming. I'll stay around for a few more minutes in case you have questions, but thanks so much for being a great class. And I hope everything goes good for your exam. You guys deserve to pass. You've been studying so hard. So, so thanks so much. Have a great one. And yeah, please let me know how things go with your tests. Appreciate it.